Welcome to this CCNA study and relaxation session. This video has been created for easy listening, whether you're studying, winding down, or even falling asleep. The pace is gentle, the tone is calm, and the content is designed to help the information settle in naturally. We'll move through the material in a clear and simple order. First, we'll explore Cisco IOS commands, walking through the basics of how network devices are configured and managed. Next, we'll cover well-known port numbers, the essential mappings between applications and protocols that every network engineer should recognize. From there, we'll go step by step through the official CCNA exam objectives. This section follows the Cisco blueprint in order, so you can hear every topic exactly as it appears in the exam guide. After that, we'll move into scenarios and deep dives. These sections provide practical explanations of how concepts come together in real networks, along with extended theory to reinforce your understanding. All of this is presented in a calm and steady rhythm, so you can listen, learn, and relax at the same time. Before we dive into the command walkthroughs, let's take a moment to talk about Cisco IOS itself. Cisco IOS, short for Inter-Network Operating System, is the software that runs on most Cisco routers and switches. It provides the command line interface, or CLI, that administrators use to configure, monitor, and troubleshoot devices. Learning iOS is an essential part of preparing for the CCNA exam. Almost every task, from assigning IP addresses to creating VLANs to configuring routing protocols, is performed through iOS commands. At first, the command line can feel intimidating, but Cisco IOS is designed in a logical way with modes, prompts, and a built-in help system that guides you as you work. Once you learn the basic structure, it becomes second nature. In the next sections, we'll walk step by step through the most important commands, grouped by purpose. By the end, you'll feel comfortable navigating iOS, configuring devices, and verifying your work. All skills you'll need both for the exam and for real-world networking. When you first connect to a Cisco device, you begin in user exec mode. This mode is limited. It allows only basic monitoring commands. You'll notice the prompt ends with a greater than symbol. To move deeper, you type enable, which brings you into privileged exec mode. The prompt changes to a hash symbol. In this mode, you have access to more powerful commands, including the ability to view detailed configurations and run troubleshooting tools. From here, you can enter global configuration mode with the command configure terminal. The prompt changes again, showing config in parentheses. This is where you can make changes to the running configuration of the device. Inside global configuration mode, you can step into sub-configuration modes. For example, typing interface, Gigabit Ethernet 00 places you into interface configuration mode, where you can assign IP addresses or enable the port. At any time, you can type exit to return to the previous level or end to return directly to privileged exec mode. If you want to go all the way back to user exec, use the command disable. Finally, Cisco IOS has a built-in help system. Typing a question mark shows available commands, and adding it after a keyword displays valid options. This makes navigation easier, even if you don't remember the full syntax. Once you're comfortable moving around Cisco IOS, the next step is learning how to perform a basic device setup. These are the foundational tasks that prepare a router or switch for use on a network. One of the first steps is giving the device a host name. By default, most devices are named router or switch, but you can set a custom name with the hostname command. This makes it easier to identify the device when you're working with multiple systems. Next, you'll want to configure passwords. On Cisco IOS, you can secure access in several places. The console line, which protects local logins through the console port. The VTY lines, which protect remote access through Telnet or SSH. And the enable password or enable secret, which protects privileged exec mode. The enable secret is preferred since it's stored in an encrypted form. Another key step is configuring interfaces. Entering interface configuration mode with a command like interface Gigabit Ethernet 00 allows you to assign an IP address and enable the port with no shutdown. Without this, the interface stays administratively down. Finally, once the device is set up, you should save the configuration. By default, changes are stored in the running configuration, which is lost if the device reboots. Use the command copy running-config startup config to save it permanently. Once a device is configured, The next step is to verify that everything is working as expected. Cisco IOS provides a wide range of show commands that let you check status, review configurations, and troubleshow issues. One of the most common is show running config, which displays the active configuration currently in memory. To see what will be applied after a reboot, you can use show startup config. The command show version provides useful information about the device itself, including the iOS software version, system uptime, and hardware details. For quick interface checks, show IP interface brief is a favorite. It lists interfaces, their IP addresses, and whether they are administratively up or physically connected. To see information about neighboring Cisco devices, you can use show CDP neighbors. For switches, show MAC address table displays learned MAC addresses, and show VLAN brief lists configured VLANs and their status. When working with routers, show IP route is essential. It displays the routing table, showing which networks are known and how they were learned. Even with careful planning, networks don't always behave as expected. That's why Cisco IOS includes built-in troubleshooting tools to help diagnose and resolve issues quickly. One of the simplest is ping. This command sends ICMP echo requests to a destination and checks whether replies come back. A successful ping shows that the device can reach the destination, while failures point to connectivity problems. For more detail, you can use traceroute. Instead of just confirming reachability, traceroute shows the path packets take through the network. It lists each router along the way and where delays or failures occur. The show log command displays system messages, including interface status changes, configuration events, and error notifications. Logs provide valuable context when troubleshooting intermittent problems. Another powerful tool is debug. Debug commands display real-time information about specific processes, such as routing protocols or packet handling. While extremely useful, debug should be used carefully, since it can generate a lot of output and affect device performance. To stop it, the command undebug all, or simply uall, clears all active debugging. Finally, counters can be checked with show interface. This shows statistics such as errors, collisions, and drops, helping you identify physical or configuration issues on an interface. Before we dive into the list of well-known port numbers, let's take a moment to explain what ports are and why they matter. In networking, a port is like a doorway into a device. When data travels over TCP or UDP, the port number tells the system which service or application the traffic belongs to. For example, web traffic typically uses port 80 or 443, while email might use ports like 25 or 143. The Internet Assigned Numbers Authority, or IANA, keeps a registry of these ports. The range from 0 to 1N23 is known as the well-known ports, and many networking services rely on them. Knowing these ports is essential for troubleshooting, configuring firewalls, and of course for the CCNA exam. Now let's begin with our first category, remote access and management. Telnet uses port 23. It allows remote access to devices but sends data in clear text, which makes it insecure. For this reason, it has largely been replaced. SSH, or Secure Shell, uses port 22. It provides encrypted remote management and is the preferred alternative to Telnet. RDP, or Remote Desktop Protocol, uses port 3389. This is most often associated with Windows systems for graphical remote access. Management also includes web-based access. HTTP uses port 80 for unencrypted web traffic. HTTPS uses port 443, which adds encryption through TLS or SSL, making it the standard for secure web communication. For monitoring and device management, SNMP uses port 161, with port 162 reserved for traps and alerts. SNMP is commonly used to monitor network devices. Syslog uses port 514 to send system messages to a centralized server. TACAX Plus uses port 49, and Radius uses ports 1812 and 1813. Both are used for authentication, authorization, and accounting in secure network environments. The next group of well-known ports covers file transfer and sharing services. These ports are used whenever data needs to be moved between systems, whether it's a configuration file, an operating system image, or user data. FTP, the file transfer protocol, uses ports 20 and 21. Port 21 is the control channel, while port 20 is used for data transfer. FTP allows file uploads and downloads, but by default, it is not secure. FTPS uses ports 989 and 990. This is the secure version of FTP, adding encryption to protect the data as it moves across the network. SFTP, or SSH File Transfer Protocol, runs over port 22. Despite the name, it is not related to FTP directly. Instead, it's built into SSH and provides secure file transfers using the same encrypted session. TFTP, or Trivial File Transfer Protocol, uses port 69. TFTP is very lightweight and does not use authentication or encryption. Because of its simplicity, it is often used on Cisco devices for transferring configuration files or iOS images. SMB, or Server Message Block, uses port 445. This protocol is primarily used in Windows environments for file and printer sharing across the network. NFS, or Network File System, uses port 2049. It is commonly used in Unix and Linux environments to share files and directories over the network. The next group of ports is used for email and messaging services. These protocols handle how messages are sent, received, and accessed by users across a network. SMTP, or Simple Mail Transfer Protocol, uses port 25. This is the original port for sending email between mail servers. However, because of spam and security issues, many systems now use alternate ports for client submission. Port 465, sometimes called SMTPS, was historically used for sending email securely over SSL. While it was deprecated for a time, it is still widely supported. Port 587 is the modern standard for email submission. Clients use this port, often with Start TLS encryption, to send outbound messages through a mail server. For retrieving email, two major protocols are used. POP3, or Post Office Protocol version 3, uses port 110. POP3 downloads messages from the server to the client, usually removing them from the server in the process. IMAP, or Internet Message Access Protocol, uses port 143. IMAP keeps email on the server and allows clients to synchronize messages across multiple devices. Both POP3 and IMAP also have secure versions. Port 995 is POP3S, the encrypted version of POP3. Port 993 is IMAPS, the encrypted version of IMAP. In summary, email and messaging ports include SMTP on 25, SMTPs on 465, submission on 587, POP3 on 110, POP3S on 995, IMAP on 143, and IMAPS on 993. These ports define how email is sent, stored, and retrieved securely across the network. This group of ports is dedicated to name resolution and core network infrastructure services. These are the background protocols that keep networks running smoothly. DNS, or Domain Name System, uses port 53. DNS translates human-friendly names like example.com into IP addresses. It works over both TCP and UDP depending on the type of query. DHCP, or Dynamic Host Configuration Protocol, uses ports 67 and 68. Port 67 is used by the server, and port 68 is used by the client. DHCP automatically assigns IP addresses and network settings, making it essential for day-to-day connectivity. BootP also uses ports 67 and 68. It is an older protocol that DHCP was built upon, and while mostly obsolete, it can still appear in legacy environments. LDAP, or Lightweight Directory Access Protocol, uses port 389. LDAP is used to access and maintain directory services, such as user and device information. LDAPS, the secure version of LDAP, uses port 636. It adds encryption to protect sensitive directory queries and responses. Kerberos uses port 88. This protocol is widely used for secure authentication in Active Directory environments and supports single sign-on across multiple services. In summary, name resolution and infrastructure ports include DNS on 53, DHCP and BootP on 67 and 68, LDAP on 389, LDAPs on 636, and Kerberos on 88. These ports ensure devices can find each other, authenticate users, and automatically receive configuration details. Our final group of ports covers specialized services and applications. These are not always used in every network, but they are important to understand for the CCNA exam and for real-world operations. NTP, or Network Time Protocol, uses port 123. NTP keeps devices synchronized with accurate time, which is critical for logging, authentication, and coordination of events. SQL services also have dedicated ports. Microsoft SQL Server commonly uses port 1433. MySQL uses port 3306. Oracle databases often use port 1521. These ports allow applications to connect to databases and query information. VPN services rely on several ports and protocols. IPsec uses port 500 for IKE, the Internet Key Exchange process. It also uses port 4500 when NAT traversal is required. The actual encrypted data is carried by ESP, which is protocol 50, not a port. SIP, or Session Initiation Protocol, uses port 5060 for unencrypted traffic and 5061 for secure traffic. SIP is widely used for initiating and managing VoIP calls. RTP, or Real-Time Transport Protocol, uses a dynamic range of ports, typically 16,384 through 32,767. RTP carries the actual voice or video media streams for VoIP and video conferencing. In this section, we'll walk through the official exam objectives for the Cisco Certified Network Associate exam. We'll go step by step, following them in order, so you can hear every topic in the same sequence you'll find on the official blueprint. Each domain of the exam carries a specific weight toward your final score. By knowing these percentages, you'll understand which areas deserve more of your study time. Network fundamentals make up about 20% of the exam. This includes the basics of networking devices, topologies, cabling, and addressing. Network access counts for around 20% as well. This area covers switching, VLANs, spanning tree, and wireless principles. IP connectivity makes up about 25%, the single largest section. This domain focuses on routing, routing tables, static and dynamic routing, and related concepts. IP services account for about 10%. These include NAT, DHCP, NTP, and other core services that support a functioning network. Security fundamentals represent about 15% of the exam. Here you'll find topics like ACLs, device security, VPNs, and common security practices. And finally, automation and programmability make up around 10%. This section introduces concepts like controller-based networking, APIs, and configuration management tools. We'll cover each of these domains in order, starting with network fundamentals, and we'll touch on every single exam objective along the way. Routers are the devices that sit at the boundaries of networks and decide where data should go. Think of them as traffic directors, watching packets arrive and forwarding them to the correct next hop. At their core, routers operate at layer 3 of the OSI model, the network layer. This is the layer where IP addressing lives. When a packet arrives, the router looks at its destination IP address and consults its routing table to choose the best path forward. Unlike switches, which connect devices within the same local area network, routers connect different networks together. They allow communication between subnets, between LANs and WANs, and even out to the wider internet. Routers can make decisions based on static routes, which are configured manually by administrators, or dynamic routing protocols like OSPF, EIGRP, or BGP, which allow routers to exchange information and discover new paths automatically. Routers also provide important services. They can perform network address translation, NAT, allowing private IP addresses inside a network to share a single public address on the outside. They can act as a DHCP relay, passing requests from clients to a central DHCP server. And they enforce security through access control lists, filtering traffic, and protecting internal resources. When you think of a router, picture a gateway, a doorway that data must pass through to leave one network and reach another. It is that guardian at the edge, making sure every packet knows the correct path forward. That is the role of the router, the foundation of connectivity between networks. Switches are devices used to connect multiple hosts within the same local area network. They forward frames based on MAC addresses, and they operate primarily at layer 2 of the OSI model. A layer 2 switch learns which devices are connected to each of its ports by examining the source MAC addresses of incoming frames. It builds a MAC address table and then forwards frames only to the port where the destination device is located. This reduces unnecessary traffic and increases efficiency. Layer 2 switches support features like VLANs, allowing a single physical switch to be divided into multiple logical networks. Trunk links can then carry traffic for multiple VLANs across switches using protocols such as 802.1q. A Layer 3 switch combines the capabilities of a Layer 2 switch with basic routing functions. It can forward traffic not just based on MAC addresses, but also based on IP addresses. This allows it to perform inter-VLAN routing, enabling devices in different VLANs to communicate without needing a separate external router. While routers are still essential at the edge of networks and for connecting to the internet, Layer 3 switches provide high-speed routing within a LAN environment. In summary, Layer 2 switches forward traffic based on MAC addresses within the same network, while Layer 3 switches extend that functionality by routing between different networks at high speeds. Next-generation firewalls, or NGFWs, are advanced security devices that go beyond traditional firewalls. They inspect traffic at multiple levels, not just IP addresses and ports, but also applications, users, and content. NGFWs provide deeper visibility into network traffic by identifying the application behind each packet. This allows more granular control. For instance, you can block specific application features, like peer-to-peer file sharing, while allowing others to pass through. They also integrate with identity systems, allowing rules based on users or user groups instead of just IP addresses. This means security policies can be tied to individuals or roles within an organization. Intrusion prevention systems, or IPS, are often built into NGFWs. An IPS analyzes network traffic in real time and looks for suspicious patterns. When it detects a threat, the IPS can take immediate action, such as dropping the packet, resetting the connection, or generating an alert. NGFWs and IPS technologies work together to provide layered defense. They can block known threats using signature-based detection and defend against unknown threats using behavior or anomaly-based detection. NGFWs also include features like SSL/TLS decryption, allowing them to inspect encrypted traffic for hidden threats. This makes them more effective against modern attacks that use encrypted channels. In short, next-generation firewalls combine traditional firewall functionality with identity awareness, application-level filtering, encryption inspection, and integrated intrusion prevention, all in a unified device. Access points are devices that extend a wired network into a wireless network. They allow laptops, phones, tablets, and other wireless devices to connect to the LAN without physical cables. At their core, access points operate at Layer 2, bridging wireless clients into the wired network. They use radio frequencies to transmit and receive data, translating it into Ethernet frames on the wired side. Access points broadcast one or more service set identifiers, or SSIDs. These are the names that wireless clients see when searching for available Wi-Fi networks. Each SSID can map to a VLAN, providing logical separation of traffic. Modern access points support multiple frequency bands, such as 2.4 GHz and 5 GHz, and newer models also support 6 GHz with Wi-Fi 6E. This provides more channels and reduces interference. Access points can operate in two main modes. In autonomous mode, each access point is configured and managed individually. In controller-based mode, access points are managed centrally by a wireless LAN controller, which handles configuration, roaming, and policy enforcement. Security on access points is critical. They support encryption methods such as WPA2 and WPA3, ensuring that wireless communications are protected against unauthorized access. Controllers are devices or software systems that centralize the management of a network. Instead of configuring each device individually, a controller provides a single point of control for policies, configurations, and monitoring. In wireless networks, a wireless LAN controller, or WLC, manages multiple access points. The controller handles tasks like channel assignment, transmit power levels, security settings, and seamless roaming between access points. This makes the wireless network easier to scale and maintain. In software-defined networking, controllers separate the control plane from the data plane. Network devices such as switches and routers forward traffic, while the controller makes centralized decisions about how that traffic should flow. Controllers communicate with network devices through southbound APIs, such as OpenFlow or NetConf. At the same time, controllers expose northbound APIs that allow applications to request network services or retrieve information. Cisco's DNA Center is an example of a network controller. It provides automation, assurance, and policy-based management for both wired and wireless infrastructure. The benefit of using controllers is consistency. Configurations and security policies are applied across the entire network from a central point. This reduces complexity, saves time, and lowers the risk of misconfiguration. Endpoints are the devices at the edge of a network that people and systems use to communicate. They are the sources and destinations of network traffic. Common examples of endpoints include desktops, laptops, servers, smartphones, tablets, IP phones, and IoT devices such as cameras and sensors. Each of these devices connects to the network to send or receive data. Endpoints are typically assigned an IP address, which uniquely identifies them on the network. They also have a MAC address, which identifies their network interface card at layer 2. The security of endpoints is critical because they are often the target of attacks. Antivirus software, endpoint detection and response, and proper patching help protect them from compromise. Endpoints can connect through wired Ethernet, wireless access points, or even cellular connections, depending on their role and mobility needs. In modern enterprise networks, endpoints are often authenticated using protocols like 802.1x, which ensures only trusted devices can access the network. In summary, endpoints are the devices that people and applications use to access network resources, making them a vital part of every network and a critical focus for both connectivity and security. Servers are powerful computers that provide resources, services, and applications to other devices on the network. Unlike endpoints, which primarily consume resources, servers are designed to share and deliver them. Common types of servers include file servers, which store and share data, web servers, which deliver web pages and applications, email servers, which handle communication, and database servers, which manage structured data for applications. Servers often run specialized operating systems that are optimized for performance, security, and reliability. Examples include Windows Server, various Linux distributions, and Unix-based systems. In most networks, servers are centralized in data centers or cloud environments. This centralization makes them easier to maintain, back up, and secure. Servers usually have more processing power, memory, and storage than typical endpoints. They are also designed with redundancy in mind, using features like RAID storage, redundant power supplies, and failover clustering to ensure high availability. Virtualization allows a single physical server to host multiple virtual machines, each acting as an independent server. This increases efficiency and flexibility. Cloud providers take this further by offering server resources on demand without requiring organizations to maintain their own hardware. Power over Ethernet, or PoE, is a technology that allows network cables to carry electrical power alongside data. This enables devices like access points, IP phones, and cameras to receive both power and network connectivity using a single Ethernet cable. PoE works by sending a low-voltage DC current over the unused pairs of an Ethernet cable or by injecting power into the data pairs. This power is delivered from a power sourcing equipment, PSE, typically a PoE-enabled switch or an inline power injector, to a powered device, PD, such as a wireless access point or IP camera. There are several PoE standards, each providing increasing power budgets. IEEE 802.3AF PoE delivers up to 15.4 watts per port. IEEE 838T PoE Plus increases the capacity to 30 watts. IEEE 802 Plus or 4P PoE supports up to 60 to 100 watts, enabling high-power devices like pan-tilt zoom cameras or even laptops. PoE simplifies installation and reduces costs. You don't need a separate power outlet near each device. Instead, network devices can be powered from centralized wiring closets or switches. This is especially useful in areas where power infrastructure is limited or hard to reach. PoE also supports safety mechanisms. Devices negotiate power requirements before being powered, ensuring that incompatible devices aren't forced to accept power. Additionally, PoE switches monitor power consumption and can shut down ports if power is exceeded, protecting both the switch and connected devices. In summary, PoE enables efficient, flexible deployment of network devices by combining power and data delivery over a single cable. It simplifies installations and supports a range of powered devices in modern networks. The two-tier network architecture is a common design used in enterprise networks. It is also known as the collapsed core architecture because it reduces the traditional three-tier model into just two functional layers. The first layer is the access layer. This is where end devices connect to the network. Switches at the access layer provide connectivity for endpoints like PCs, phones, cameras, and wireless access points. The second layer is the distribution layer. This layer aggregates the access switches, provides policy enforcement, and connects users to other parts of the network. It often includes routing functions, redundancy, and load balancing. By combining the distribution and core functions into a single layer, the two-tier model simplifies the design. It reduces hardware costs, lowers complexity, and makes management easier for small to medium-sized networks. However, in very large networks, the two-tier approach may not scale as well. That is where the three-tier model with a dedicated core becomes useful. In summary, the two-tier architecture provides a balance between simplicity and performance. It's a practical design for many modern enterprise environments, delivering both access and distribution functions with efficiency. The three-tier network architecture is a classic design used in larger enterprise networks. It is built on three functional layers: the core layer, the distribution layer, and the access layer. At the bottom is the access layer. This is where endpoints connect to the network. Switches at this layer provide connectivity for devices such as computers, phones, and access points. Above the access layer is the distribution layer. Distribution switches aggregate multiple access switches. This layer provides routing between VLANs, enforces security policies, and often includes redundancy for high availability. At the top is the core layer. The core provides fast, reliable transport between distribution blocks. Its job is to move large amounts of data quickly and efficiently across the network. The core should be highly available with minimal latency and maximum throughput. The three-tier model is designed to scale. By separating functions into dedicated layers, it allows large enterprise networks to grow while maintaining performance and manageability. The spine leaf architecture is a modern network design commonly used in data centers. It is built to provide predictable performance, high bandwidth, and low latency for east-west traffic, where servers and applications need to communicate directly with each other. In this design, there are two types of switches: spine switches and leaf switches. Leaf switches are at the access layer. They connect directly to servers, storage devices, and other endpoints. Spine switches form the backbone of the network. Every leaf switch connects to every spine switch, creating a full mesh. This ensures that any device connected to a leaf can reach any other device with the same predictable number of hops. Unlike the traditional three-tier model, spine leaf has no dedicated core or distribution layers. Instead, the equal connectivity between spines and leaves eliminates bottlenecks and provides consistent performance. This architecture is highly scalable. As more servers are added, additional leaf switches can be introduced. If more bandwidth is needed, more spine switches can be added without disrupting the existing design. WAN is a network that spans large geographic areas. While a local area network connects devices within a single building or campus, a WAN connects networks across cities, countries, or even continents. WANs make it possible for branch offices, remote workers, and data centers to communicate as if they were part of the same enterprise network. They rely on service providers to deliver connectivity using public or private infrastructure. Common WAN technologies include MPLS, Metro Ethernet, broadband internet, and VPNs built over public internet connections. Increasingly, enterprises are adopting SD-WAN, which uses software-defined policies to intelligently route traffic across multiple WAN links. WAN links often connect through routers, which manage the flow of traffic between local networks and the service provider's network. Redundancy and failover are important considerations, since WAN connectivity is critical to business operations. SOHO network is designed to provide reliable connectivity for a small number of users and devices. These networks are common in remote work environments, small businesses, and home offices. SOHO networks typically use a single multifunction device, often called a residential gateway or wireless router. This device combines routing, switching, wireless access, and firewall features into one unit. It connects the local network to the internet service provider, while also providing wireless coverage for laptops, phones, and other devices. Wired connections are still common in SOHO networks, especially for desktop computers, printers, and network storage. Wireless connectivity provides flexibility and mobility for other devices. Security is an important consideration. SOHO routers typically include features such as network address translation, or NAT, to share a single public IP address, and firewall capabilities to block unwanted traffic from the internet. Compared to enterprise networks, SOHO networks are simpler, less expensive, and easier to manage. They are not designed for the same scale or performance, but they provide the essential services needed for small environments. On-premises networks are built and managed within an organization's own facilities. All of the equipment, such as switches, routers, servers, and firewalls, is installed locally and managed directly by the IT staff. This provides complete control over performance, security, and customization. However, it also requires ongoing maintenance, hardware upgrades, and physical space to support the infrastructure. Cloud networking, by contrast, delivers services through a provider's infrastructure. Applications, storage, and even networking functions are hosted in remote data centers and accessed over the internet or through dedicated connections. Cloud services can be public, private, or hybrid, depending on the needs of the organization. A public cloud offers resources on shared infrastructure managed by providers such as Amazon Web Services, Microsoft Azure, or Google Cloud. A private cloud delivers similar benefits but is dedicated to a single organization. A hybrid cloud combines on-premises infrastructure with public or private cloud services, offering flexibility and scalability. The choice between on-premises and cloud depends on factors such as cost, scalability, security requirements, and management preferences. Many modern networks use a hybrid model to balance the control of on-premises systems with the agility of cloud services. Comparing single-mode fiber, multi-mode fiber, and copper networks can use different types of physical media to transmit data. The three most common are single-mode fiber, multi-mode fiber, and copper cabling. Each has different characteristics, advantages, and use cases. Single-mode fiber uses a very small core, about 9 microns in diameter. It carries light from a laser source in a single path or mode, which minimizes signal distortion. Because of this, single-mode fiber supports extremely long distances, tens of kilometers, at very high speeds. It is often used in service provider networks, data center interconnects, and long-haul connections. Multi-mode fiber has a larger core, typically 50 or 62.5 microns, and it allows light from an LED source to travel in multiple paths or modes. This makes multi-mode fiber less expensive than single-mode, but also more limited in distance, usually up to a few hundred meters depending on the speed. It is common in enterprise LANs and data centers where shorter runs are typical. Copper cabling, such as twisted pair Ethernet cables, carries electrical signals rather than light. It is inexpensive, easy to install, and widely used in access networks to connect endpoints like computers, phones, and printers. Copper supports distances up to 100 meters for most Ethernet standards. Higher speeds and longer runs can be achieved with shielding and advanced designs, but copper is more susceptible to interference than fiber. Ethernet shared media and point-to-point. Ethernet networks can operate using different types of connection models. Two common ones are shared media and point-to-point connections. In a shared media environment, multiple devices use the same communication medium. Early Ethernet networks used coaxial cables or hubs, where all devices shared the same bandwidth. Only one device could transmit at a time, and collisions occurred when two devices sent data simultaneously. To manage this, Ethernet relied on the carrier sense multiple access with collision detection method, known as CSMA-CD. Shared media is largely obsolete today, but it is important to understand as part of Ethernet's history. A point-to-point connection is a direct link between two devices. In modern Ethernet, this usually means a dedicated twisted pair or fiber optic cable between a switch and an endpoint, or between two switches. Because the link is exclusive to those two devices, there are no collisions, and full duplex communication is possible. This allows both devices to send and receive data at the same time, providing higher performance and reliability. Network performance problems are often caused by physical layer or interface issues. Common examples include collisions, errors, duplex mismatches, and speed mismatches. Collisions occur when two devices transmit on the same medium at the same time. This was common in older Ethernet shared media environments, but in today's switched full duplex networks, collisions are rare. If they do appear, it usually indicates a misconfiguration or faulty hardware. Errors can take many forms, such as CRC errors, runts, giants, or framing errors. These typically result from poor cabling, electrical interference, or damaged connectors. Monitoring error counters on switch or router interfaces can help identify these problems. Duplex mismatch happens when one side of a link is set to full duplex, while the other side is set to half duplex. This causes collisions and late collisions, leading to degraded performance. Ensuring both ends of the connection have matching duplex settings prevents this issue. Speed mismatch occurs when two connected devices are configured for different speeds, such as one at 100 megabits and the other at 1 gigabit. This can prevent the link from establishing or cause instability. Using auto-negotiation or manually matching speeds at both ends avoids this problem. TCP and UDP are two of the most common transport layer protocols. Both are built on top of IP, but they serve different purposes and behave in very different ways. Transmission Control Protocol, or TCP, is connection-oriented. It establishes a session between two devices before data is exchanged. TCP ensures reliable delivery by sequencing packets, acknowledging receipt, and retransmitting lost segments. This makes it suitable for applications where accuracy is more important than speed, such as web browsing, email, and file transfers. TCP also provides flow control and congestion control, adjusting transmission rates to avoid overwhelming the network. User Datagram Protocol, or UDP, is connectionless. It sends packets called datagrams without first establishing a session and without tracking delivery. There are no acknowledgments, sequencing, or retransmissions. This makes UDP faster and more efficient, but less reliable than TCP. It is used for applications where speed and low latency are more important than guaranteed delivery, such as voice over IP, video streaming, and online gaming. IPv4 addressing is the foundation of network communication. Every device on a network must have a unique IP address to send and receive data. An IPv4 address is a 32-bit number, usually written in dotted decimal format, such as 192.168.10. To configure an IPv4 address on a device, you also need a subnet mask. The subnet mask identifies which part of the address represents the network and which part represents the host. For example, with an address of 192.168.1.10 and a subnet mask of 255.255.255.0, the first three octets identify the network, and the last octet identifies the host within that network. Subnetting divides larger networks into smaller subnetworks. This improves efficiency, reduces wasted addresses, and increases security and manageability. Subnetting is often expressed using prefix length notation. For instance, 192.168.1.0/24 means that the first 24 bits are reserved for the network portion. Verification is an important step. On Cisco devices, commands such as show IP interface brief can be used to confirm that an address has been assigned and that the interface is up. Tools like ping and traceroute can test connectivity and confirm that devices are reachable across the network. Private IPv4 addressing is a system of reserved IP address ranges that are not routable on the public internet. They are designed to be used inside local networks, such as homes, offices, and enterprise LANs. The Internet Assigned Numbers Authority, or IANA, set aside three main ranges for private use: NASH 10.0.0.0 to 10.255.255.255, known as the 10.0.0/8 block; 172.6.0.0 to 172.31.255.255, the 172.168.0.0's 12 block; 192.168.0.0 to 192.168.25.255, the 192.0.0 16 block. Any device can use addresses in these ranges inside a private network, but because they are not globally unique, they cannot be routed over the internet. Instead, when private addresses need internet access, they are translated into public addresses using Network Address Translation, or NAT. Private addressing conserves the limited IPv4 address space and provides a level of isolation between internal and external networks. It also allows organizations to freely design their internal address schemes without needing approval from a central authority. IPv6 was developed to overcome the limitations of IPv4, providing a much larger address space and improved efficiency. An IPv6 address is 128 bits long, written in hexadecimal, and separated by colons. To make addresses easier to work with, IPv6 allows you to shorten them. Leading zeros can be removed, and long strings of consecutive zeros can be compressed using a double colon. When configuring IPv6, each device is assigned both an address and a prefix length. The prefix length determines how much of the address represents the network portion. For example, a prefix length of 64 is the most common, meaning the first half of the address identifies the network, while the second half identifies the host. IPv6 supports several address types. Global unicast addresses are publicly routable. Link local addresses are automatically generated and used for communication on the local link. Multicast addresses identify groups of devices. Anycast addresses can be assigned to multiple devices, with traffic delivered to the nearest one. To verify IPv6 configuration on Cisco devices, you can use commands that display interface status and assigned addresses. Connectivity can be tested with familiar tools such as ping and traceroute, adapted for IPv6. In IPv6, a unicast address identifies a single unique device on the network. Traffic sent to a unicast address is delivered to that one device only. There are three main types of unicast addresses: global unicast, unique local, and link local. Global unicast addresses are similar to public IPv4 addresses. They are globally routable and reachable across the internet. Devices with global unicast addresses can communicate with any other device in the world, provided routing is in place. Unique local addresses are similar to private IPv4 addresses. They are not routable on the public internet, but are used within an organization. They provide internal communication without conflicting with global addresses. Link local addresses are automatically assigned to every IPv6 enabled interface. They are used for communication between devices on the same local link. Routing protocols and neighbor discovery rely on link local addresses, making them essential even when other IPv6 addresses are present. An anycast address in IPv6 is assigned to multiple devices, but traffic sent to that address is delivered to only one of them, specifically the one that is closest in terms of routing distance. Anycast is often used to provide services in a distributed way. For example, multiple servers across different locations may share the same anycast address. When a client sends traffic to that address, the network automatically directs it to the nearest server. This improves performance and reduces latency. Routers use their routing tables to decide which device holding the anycast address is closest. If one server becomes unavailable, the routing system will automatically redirect traffic to the next nearest server, improving reliability and resilience. Common uses of anycast include load distribution for DNS services, content delivery networks, and global internet infrastructure. A multicast address in IPv6 is used to send traffic to a group of devices at the same time. Instead of delivering packets to every device on a network, multicast ensures that only devices that are interested in receiving the traffic will process it. Multicast improves efficiency. For example, when streaming video or sending routing updates, one packet can be delivered to many receivers without duplicating the data for each one individually. IPv6 multicast addresses begin with a reserved prefix that identifies them as multicast. Devices join a multicast group when they need to receive specific traffic. Once joined, they listen for packets sent to that multicast address. Multicast is heavily used by IPv6 itself. Protocols like neighbor discovery and routing protocols rely on multicast groups for efficient communication. In summary, multicast addresses allow one-to-many communication, saving bandwidth and ensuring that traffic is delivered only to devices that request it. This makes multicast an essential part of IPv6 networking. Modified EUI64 is a method used in IPv6 to automatically create an interface identifier, which forms the host portion of an IPv6 address. Normally, IPv6 addresses are made up of two parts, the network prefix and the interface identifier. The interface identifier is typically 64 bits long. With modified EUI64, a device can generate this identifier from its own hardware address, such as the MAC address. The process works by splitting the 48-bit MAC address into two halves, inserting a fixed value in the middle, and then flipping a specific bit to indicate that the address is universally unique. This results in a 64-bit identifier that can be combined with the network prefix to form a complete IPv6 address. The benefit of modified EUI64 is that devices can automatically configure their IPv6 addresses without needing manual assignment or a DHCP server. This supports a feature known as stateless address auto-configuration. However, because the interface identifier is based on the hardware address, it can also reveal information about the device manufacturer and create privacy concerns. To address this, IPv6 also supports random or temporary interface identifiers that change over time. Every client device on a network needs to be configured with correct IP parameters in order to communicate. These parameters include the device's IP address, the subnet mask or prefix length, the default gateway, and the DNS servers. On Windows systems, the command ipconfig displays the current IP configuration. It shows the assigned IPv4 and IPv6 addresses, the subnet mask, the default gateway, and the DNS servers in use. To test connectivity, commands such as ping, tracert, and nslookup can be used. On macOS and Linux systems, the command ifconfig or the more modern IP adder shows the assigned addresses and interface status. The command IP route can be used to view the routing table and verify the default gateway. Tools like ping, traceroute, and dig are also available for testing connectivity and name resolution. Verifying IP parameters ensures that the device is correctly connected to the network using the proper address, gateway, and DNS settings. If parameters are missing or incorrect, the client will not be able to reach local or remote resources. Wireless networks operate using radio frequencies, and these frequencies are divided into channels. To avoid interference, it is important to understand which channels can be used without overlapping each other. In the 2.4 GHz band, Wi-Fi provides 11 channels in many regions, but only 3 of them are non-overlapping. These are channels 1, 6, and 11. Using these 3 ensures that signals do not interfere with each other, which is critical in dense environments. In the 5 GHz band, there are many more channels available, and they are spaced further apart. This allows for a larger number of non-overlapping channels, giving networks more flexibility and reducing congestion. The newer 6 GHz band, introduced with Wi-Fi 6E, offers even more spectrum. This provides additional non-overlapping channels and helps support high-density deployments and high-bandwidth applications. Choosing non-overlapping channels improves performance by reducing interference between nearby access points. This results in stronger connections, higher throughput, and a better user experience. An SSID, or Service Set Identifier, is the name of a wireless network. It is what users see when they search for available Wi-Fi connections on their devices. Access points broadcast one or more SSIDs to identify the networks they provide. Each SSID can be mapped to a specific VLAN, allowing separation of traffic. For example, one SSID might be used for employees, another for guests, and a third for IoT devices. SSID broadcasting can be enabled or disabled. When enabled, the network name is visible to anyone scanning for Wi-Fi. When disabled, the SSID is hidden, but clients can still connect if they are configured with the correct name. Security policies are often tied to SSIDs. Authentication methods such as WPA2 or WA3 can be applied per SSID, ensuring that only authorized users gain access. RF, or radio frequency, is the medium that wireless networks use to transmit data. Instead of electrical signals traveling through cables, Wi-Fi relies on radio waves to carry information between devices and access points. Radio waves are measured in frequency, expressed in hertz. Wi-Fi most commonly uses the 2.4 GHz, 5 GHz, and now the 6 GHz frequency bands. Each band offers different trade-offs. The lower frequencies travel farther and penetrate walls better, while the higher frequencies support faster speeds but shorter ranges. RF signals are also measured in terms of wavelength and power. Stronger signals provide better performance, but excessive power can cause interference. Careful planning of access point placement, channel selection, and power levels ensures optimal coverage. Wireless communication over RF is subject to challenges such as interference, attenuation, and multipath. Interference comes from other devices using the same frequencies. Attenuation reduces signal strength over distance, and multipath occurs when signals reflect off surfaces and arrive at slightly different times. Encryption in wireless networking is the process of protecting data as it travels through the air, ensuring that only authorized users can read it. Because wireless signals are broadcast openly, without encryption, anyone nearby could capture and view the traffic. Early Wi-Fi standards used wired equivalent privacy, or WEP, but it had serious weaknesses and is now considered insecure. It was replaced by Wi-Fi Protected Access, or WPA, and later WPA2 and WPA3, which used stronger encryption methods. WPA2 introduced the Advanced Encryption Standard, or AES, which became the industry standard for securing wireless traffic. WPA3 builds on this with even stronger encryption and improved protection against password guessing. Encryption is tied to the wireless SSID. Devices must share the same encryption settings and keys in order to connect. Enterprise environments often use authentication servers, such as Radius, to provide unique credentials per user. Virtualization is the process of creating multiple logical systems on top of a single physical system. It allows resources to be divided, isolated, and managed more efficiently. There are several forms of virtualization that are important to understand. Server virtualization allows a single physical server to host multiple virtual machines. Each virtual machine runs its own operating system and applications as if it were a separate physical computer. This improves hardware utilization, reduces costs, and makes scaling and recovery easier. Containers are a lighter form of virtualization. Instead of running an entire operating system for each instance, containers share the host operating system's kernel while keeping applications isolated. This makes containers faster to start, more efficient, and easier to move between environments. They are widely used in modern application development and deployment. Virtual routing and forwarding, or VRFs, provide virtualization at the network layer. A VRF allows multiple routing tables to coexist on the same router. This means that different networks can share the same physical device while remaining logically separated. VRFs are commonly used by service providers and in enterprise networks to keep traffic segmented without requiring separate hardware. Switching is the process of forwarding traffic within a local area network. Switches operate primarily at layer 2 of the OSI model, using MAC addresses to make forwarding decisions. When a frame enters a switch, the device examines the source MAC address and records which port that device is connected to. This information is stored in the MAC address table. The switch then looks at the destination MAC address to decide where to forward the frame. If the destination is known, the frame is sent only out of the correct port. If the destination is unknown, the switch floods the frame out of all ports except the one it was received on. Once the destination responds, the switch learns its location and updates the table. Switches also prevent loops in the network by using the spanning tree protocol, or STP. STP blocks redundant paths until they are needed, ensuring that broadcast traffic does not circulate endlessly. Modern switches can operate at layer 3 as well, providing routing between VLANs and supporting dynamic routing protocols. Switches use a process called MAC learning to build a table of where devices are located in the network. When a frame arrives at a switch, the switch examines the source MAC address. It records that address along with the port it came from in its MAC address table. This way, the switch learns which devices are reachable on which ports. When the switch later receives a frame with that MAC address as the destination, it can forward the traffic directly to the correct port, instead of flooding it to all ports. To keep the table accurate, switches use MAC aging. If a device does not send any traffic for a certain amount of time, its entry is removed from the table. The next time that device sends traffic, the switch will learn its location again. This aging process prevents the table from filling up with outdated information and ensures that the switch always forwards frames efficiently. Frame switching is the process a switch uses to move Ethernet frames from one port to another. When a frame arrives at a switch, the device looks at the destination MAC address. If that address is already in the switch's MAC address table, the frame is forwarded only out of the port where the destination device is located. This is called forwarding. If the destination MAC address is unknown, the switch floods the frame out of all ports except the one it came in on. This ensures the frame reaches its destination, and once the destination replies, the switch learns where that MAC address lives. Switches can also filter frames. For example, if a frame is destined for a MAC address on the same port it was received from, the switch simply drops the frame rather than sending it back out. In modern networks, switches operate at full duplex, meaning devices can send and receive simultaneously without collisions. Combined with intelligent frame switching, this provides efficient, high-speed communication within the LAN. Frame flooding occurs when a switch does not know where the destination MAC address is located. When a frame arrives and the destination is not in the switch's MAC address table, the switch has no way of knowing which port to use. To ensure delivery, it sends the frame out of all ports except the one it was received on. This process is called flooding. Flooding is also used for special types of traffic, such as broadcasts and certain multicasts, where the intent is to reach many or all devices on the network. Once the destination device responds, the switch learns its MAC address and updates the table. From that point on, the switch can forward frames directly instead of flooding them. The MAC address table, sometimes called the forwarding table or CAM table, is the database a switch uses to decide where to send frames. Each entry in the table maps a MAC address to a specific switch port. When a frame arrives, the switch checks the table to see which port the destination MAC address is associated with. If it finds a match, the frame is forwarded only out of that port. The table is built dynamically through MAC learning. Whenever a device sends a frame, the switch records the source MAC address and the port it came from. Over time, the table grows to include all active devices on the network. Entries in the table do not last forever. They are cleared after an aging timer expires, ensuring that old or inactive addresses are removed. The next time that device sends traffic, it will be relearned. If the destination MAC address is not in the table, the switch floods the frame to all ports except the incoming one. Once the destination replies, its address is added to the table. We've now covered the first domain, network fundamentals. The next domain is network access, which accounts for about 20% of the exam. In this section, the focus shifts to how devices actually connect to and access the network. Topics include VLANs and trunking, understanding the role of spanning tree in preventing loops, and wireless LAN configuration and security. Network access is where the theoretical pieces of networking start coming together with real-world switch and wireless configurations. It builds directly on the switching concepts we just covered and extends them into how networks are segmented, stabilized, and secured. A VLAN, or virtual local area network, is a way to logically segment a switch into multiple separate networks. Devices in the same VLAN can communicate directly, while devices in different VLANs require a router or layer 3 switch to communicate. VLANs in the normal range are numbered from 1 to 1005. These are the VLANs most commonly used in enterprise networks. When configuring VLANs, each port on a switch can be assigned to a specific VLAN. This means that even though devices may be physically connected to the same switch, they can be logically separated into different networks for security, performance, or organizational purposes. In many cases, VLANs need to span multiple switches. To make this work, the switches are connected by a trunk link. A trunk link allows traffic from multiple VLANs to travel between switches while keeping it separated by VLAN tags. Once VLANs are configured and trunking is enabled, verification is important. This can include checking that devices in the same VLAN, even on different switches, can communicate with each other, and confirming that devices in separate VLANs cannot communicate unless routing is in place. Access ports are switch ports that belong to a single VLAN. They are most often used to connect end devices such as computers, printers, or IP phones. A data access port carries traffic for one VLAN only. For example, if a computer is connected to an access port assigned to VLAN 10, all the traffic from that computer is tagged as belonging to VLAN 10 inside the switch. When supporting voice-over IP phones, an access port can actually carry both voice traffic and data traffic. The phone is configured with a special voice VLAN, while the computer connected through the phone uses the regular data VLAN. This way, the switch can separate and prioritize voice traffic without requiring two separate physical connections. Access ports provide a simple and reliable way to assign end devices to the right VLAN, while also supporting the additional requirements of voice networks when needed. In summary, data access ports connect end devices to a single VLAN, while voice access ports allow a phone and a computer to share the same physical port but remain logically separated for proper handling of traffic. When a new switch is powered on, all of its ports are placed into the default VLAN. On Cisco switches, this is VLAN 1. The default VLAN allows devices connected to the switch to immediately communicate with each other without any additional configuration. It's essentially the starting point for network communication on a new switch. Certain control plane traffic, like some management protocols, may also use the default VLAN unless they are reconfigured. Because of this, best practice in production networks is to avoid using VLAN 1 for user traffic. Instead, administrators create and assign devices to separate VLANs for better organization and security. VLANs create logical separation within a network, which means devices in different VLANs cannot communicate directly with each other. To enable communication between VLANs, we need inter-VLAN connectivity. This is achieved through a layer 3 device, such as a router or a multi-layer switch. The most common methods are Router on a stick. A single physical router interface is configured as a trunk and handles traffic for multiple VLANs, routing between them. Multi-layer switch routing. A switch with layer 3 capabilities can perform routing directly by assigning IP addresses to VLAN interfaces, often called SVIs, or switch virtual interfaces. Once configured, devices in different VLANs can communicate as if they were on the same network, while still maintaining the segmentation benefits of VLANs. Inter-switch connectivity is all about ensuring multiple switches can work together as one unified network. The connection between switches is usually a trunk link, which carries traffic from multiple VLANs across a single physical cable. With trunking in place, VLANs can extend from one switch to another, allowing devices in the same VLAN to communicate even when connected to different switches. Configuration typically involves setting the correct trunk encapsulation, most commonly 802.1q, and enabling trunking on the interfaces that connect the switches. Verification is an important step. This means checking that the link between the switches is up, confirming that it's operating as a trunk, and ensuring that the intended VLANs are allowed across the trunk. A quick test is to connect devices to different switches, assign them to the same VLAN, and confirm they can communicate. In summary, inter-switch connectivity ensures that the VLAN and segmentation design of a network works across multiple switches, creating one consistent and scalable environment. A trunk port is a switch port that can carry traffic from multiple VLANs at the same time. Unlike an access port, which belongs to only one VLAN, a trunk uses tagging to identify which VLAN each frame belongs to. The most common tagging standard is 802.1q, often called .1q. This standard inserts a small VLAN ID field into the Ethernet frame so the receiving switch knows which VLAN the traffic belongs to. Trunk ports are most often used between switches or between a switch and a router to extend VLANs across the network. For example, a trunk can allow VLAN 10, VLAN 20, and VLAN 30 to all pass across the same physical link. Verification includes checking that the trunk is up, that the correct VLANs are allowed on the trunk, and that devices in the same VLAN can communicate even if they are on different switches. The standard method for carrying multiple VLANs across a trunk link is called 802.1q trunking. With 802.1q, each Ethernet frame is tagged with a VLAN ID. This tag is inserted into the frame header, and it tells the receiving switch which VLAN the traffic belongs to. The tag is removed before the frame is delivered to the end device, so the process is invisible to hosts. One VLAN on a trunk is chosen as the native VLAN. Frames belonging to the native VLAN are sent without a tag. By default, Cisco switches use VLAN 1 as the native VLAN, though best practice is to change it for security reasons. 802.1q trunking allows a single physical link to carry traffic for many VLANs, which makes networks scalable and efficient. It's the key technology that allows VLANs to extend seamlessly across multiple switches. On an 802.1q trunk link, one VLAN is designated as the native VLAN. Frames belonging to this VLAN are sent across the trunk with out-of-LAN tag. By default, Cisco switches use VLAN 1 as the native VLAN. However, in practice, it's considered a best practice to change the native VLAN to another unused VLAN for security reasons. If there is a mismatch in the native VLAN configuration between two switches, it can cause problems such as traffic being misdirected or frames being dropped. That's why verifying and aligning the native VLAN on both ends of a trunk is an important step. The native VLAN is often used for network management or control traffic, but it should not carry regular user data. Keeping the native VLAN separate and consistent improves both security and stability. Layer 2 discovery protocols are used to identify neighboring devices on a network. They provide important details such as device ID, IP address, interface information, and the platform or model of the device. Cisco Discovery Protocol, or CDP, is a Cisco proprietary protocol. It runs by default on Cisco devices and allows them to share information with each other. CDP helps administrators quickly discover what devices are directly connected, making troubleshooting easier. Link Layer Discovery Protocol, or LLDP, is an open standard. It works across devices from different vendors, not just Cisco. This makes LLDP especially useful in multi-vendor environments. Configuration involves enabling or disabling CDP or LLDP on interfaces as needed. Verification commands can then display information about neighboring devices, confirming connectivity and identifying what equipment is connected to each port. Ether channel is a technology that allows multiple physical links between two devices to be bundled together into one logical connection. This increases bandwidth, provides redundancy, and simplifies management. At layer 2, Ether channel groups switch ports into a single logical link for VLAN traffic. From the perspective of the spanning tree protocol, the bundle is treated as one port, which prevents loops while still using all the links. At layer 3, Ether channel can bundle routed ports, creating a logical point-to-point connection between devices. This is often used between routers or multi-layer switches for faster and more resilient routing paths. Ether channel can be configured statically or dynamically. Dynamic configuration uses protocols such as PAGP, which is Cisco proprietary, or which is an open standard defined in IEEE 802.3 AD. These protocols negotiate the bundle and ensure consistency across links. Verification includes checking that all physical links are active in the bundle, confirming the mode of negotiation, and testing traffic flow to ensure load balancing is working. Spanning tree protocol is used to prevent loops in a layer 2 network. Without it, redundant paths between switches could cause broadcast storms and bring the network down. Rapid PVST Plus, or Rapid Per VLAN Spanning Tree Plus, is Cisco's implementation of the IEEE 802.1W standard. It improves on the original spanning tree protocol by providing faster convergence and supporting separate spanning tree instances for each VLAN. The process begins with the election of a root bridge. All switches exchange spanning tree messages called Bridge Protocol Data Units, or BPDUs. The switch with the lowest bridge ID becomes the root bridge. Each non-root switch then selects a root port, which is its best path to the root bridge. Switches also choose designated ports, which are the forwarding ports on each network segment. Other redundant ports are placed into a blocking or discarding state to prevent loops. The rapid part of Rapid PVST Plus comes from its ability to quickly transition ports to a forwarding state when network changes occur. This reduces downtime and improves resiliency. In spanning tree, the root bridge is the central reference point for the entire layer 2 topology. It is chosen through an election process, where the switch with the lowest bridge ID becomes the root bridge. To provide stability, administrators often configure a primary root bridge and a secondary root bridge as a backup, ensuring predictable network behavior. On every non-root switch, one port is selected as the root port. This is the port with the best path toward the root bridge. Only one root port exists per switch, and it always forwards traffic toward the root. Each network segment also has a designated port, which is the port responsible for forwarding traffic onto that segment. Designated ports are always in a forwarding state. Any port that is not a root port or a designated port becomes an alternate port or a backup port. These ports do not forward traffic under normal circumstances. Instead, they remain in a blocking or discarding state, ready to take over if the active path fails. In spanning tree, every switch port has both a role and a state. The role defines the port's function in the spanning tree topology, while the state describes how the port is currently operating. Port roles. The root port is the port on a non-root switch with the best path toward the root bridge. A designated port forwards traffic onto a network segment and is always in a forwarding state. Alternate ports and backup ports provide redundancy. They do not forward traffic under normal conditions, but can take over if the active path fails. Port states. Spanning tree uses port states to control how traffic flows. Forwarding. The port actively sends and receives user traffic. Learning. The port is not yet forwarding traffic, but is building the MAC address table. Listening. The port is preparing to participate in the topology, listening for BPDUs but not forwarding frames. Blocking in traditional STP or discarding in rapid STP. The port does not forward user traffic, preventing loops. With Rapid PVST Plus, ports can move quickly from discarding to forwarding, which reduces downtime when network changes occur. Port fast is a spanning tree feature that allows switch ports to transition immediately into the forwarding state without going through the normal listening and learning stages. It is designed for access ports that connect directly to end devices like computers, printers, or IP phones. Since these ports are not expected to create loops, waiting for the full spanning tree process is unnecessary and would only delay connectivity. By enabling port fast, end devices can obtain an IP address and begin communicating on the network right away, without the 30-second delay that traditional spanning tree introduces. It's important to note that port fast should never be enabled on ports that connect to other switches. Doing so could create loops in the network. Spanning tree includes several protection features that help maintain a stable, loop-free network. These features safeguard against misconfigurations and unexpected topology changes. Root guard prevents a switch port from becoming the root port. If a port with root guard enabled receives superior BPDUs, that would make its neighbor the root bridge. The port is placed into a block state. This ensures that the intended root bridge remains in control. Loop guard protects against a situation where a switch stops receiving BPDUs on a port that should be blocking. Without loop guard, the port could mistakenly move to the forwarding state and create a loop. Loop guard keeps the port in a loop inconsistent state until BPDUs are received again. BPDU filter suppresses the sending and receiving of BPDUs on a port. This is sometimes used on access ports where spanning tree participation is unnecessary. However, it should be used with caution because disabling BPDUs removes spanning tree protection on that port. BPDU guard is a safety feature typically used with port fast. If a port fast enabled access port receives a BPDU, BPU guard shuts down the port. This protects the network by ensuring that access ports cannot accidentally become part of the spanning tree topology. Cisco wireless networks can be deployed in different architectures depending on the size, complexity, and requirements of the organization. The most common is the centralized architecture, where lightweight access points connect to a wireless LAN controller. The controller manages configuration, security policies, and mobility across the network. This simplifies management and allows for scalability. Another option is the distributed or autonomous architecture, where each access point operates independently. These autonomous APs handle their own configuration and management. This approach works for small networks but becomes difficult to scale. Cisco also supports a cloud-based architecture, where management and control are handled through a cloud dashboard, such as Cisco Meraki. This allows for easy deployment and centralized visibility without requiring on-site controllers. Access points can also operate in different modes. In local mode, the AP serves clients while forwarding management and control traffic to the controller. In Flex Connect mode, the AP can locally switch traffic and continue providing connectivity even if the connection to the controller is lost, which is useful for branch offices. Other specialized modes exist, such as monitor mode for detecting rogue devices, or sniffer mode for packet analysis. A wireless LAN depends on both wireless and wired infrastructure working together. Key components include access points, wireless LAN controllers, switch ports, and link aggregation. Access points connect wireless clients to the wired network. Physically, they plug into switch ports, often using power over Ethernet, so that a separate power source isn't required. Wireless LAN controllers, or WLCs, manage multiple access points. They connect to the network core or distribution layer through switch ports, providing centralized management and policy enforcement. Access ports are used when an access point is configured for a single VLAN. In this case, all wireless client traffic belongs to that VLAN, and the AP switch port behaves like any other access port. Trunk ports are used when an access point needs to carry multiple VLANs, such as separating employee, guest, and voice traffic. The trunk allows the AP to tag frames with VLAN IDs so that traffic remains segmented across the wired network. Link aggregation groups, or LAGs, combine multiple physical links into one logical connection. A WLC can use LAG-J to increase bandwidth and redundancy between itself and the switch infrastructure, ensuring reliable performance even if a physical link fails. Network devices can be managed in several different ways depending on the level of security and the type of environment. The console port provides direct, out-of-band access to a device. It's used for initial setup, password recovery, or troubleshooting when remote access isn't available. Telnet and SSH provide in-band remote command line access. Telnet sends all data in plain text, which makes it insecure and rarely used today. SSH encrypts the session, providing a secure alternative that is the standard for remote management. HTTP and HTTPS allow management through a graphical web interface. HTTP is unencrypted and insecure, while HTTPS encrypts the session, protecting credentials and data. For centralized authentication, devices can use TACACS Plus or Radius servers. TACACS Plus is a Cisco protocol that provides detailed command authorization and accounting. Radius is an open standard that combines authentication and accounting in a single process. Both improve security by centralizing user accounts and access policies. Finally, many modern networks use cloud-managed platforms such as Cisco Meraki, where devices connect to a cloud service for configuration, monitoring, and updates. This provides centralized visibility and simplifies remote management. Wireless LAN controllers and cloud-managed platforms often provide a graphical user interface, or GUI, for configuring wireless networks. This makes setup and management more intuitive by presenting options in menus rather than requiring command line commands. The first step is usually WLAN creation. In the GUI, administrators define a wireless network by assigning it a name or SSID and mapping it to a VLAN on the wired side. This determines how wireless traffic is carried into the wired network. Next are security settings. Here, administrators choose the type of authentication and encryption, such as WPA2 or WPA3, and whether users authenticate with a pre-shared key or through enterprise methods like 802.1x with Radius. QoS profiles, or quality of service profiles, allow different types of traffic to be prioritized. For example, voice traffic can be given higher priority than web browsing to reduce latency and improve call quality. Finally, advanced settings provide fine-tuning. These may include features like band steering, load balancing across access points, client isolation, or specific roaming parameters. So far, we've looked at network fundamentals and network access. The next domain is IP connectivity, which accounts for a significant portion of the CCNA exam. This section focuses on how devices communicate beyond their local network. It covers routing concepts, the role of default gateways, and the difference between static and dynamic routing. It also includes how routers make forwarding decisions using IP addresses, routing tables, and administrative distances. Routers use a routing table to decide where to send packets. Each entry in the table contains several key pieces of information. The first component is the destination network. This identifies the network or subnet that the route applies to. Alongside it is the prefix length, which tells the router how many bits define the network portion of the address. Next is the next hop address, or the outgoing interface. The next hop address is the IP address of the next router on the path. The outgoing interface is the physical or logical port the router uses to forward the packet. Each route also has an administrative distance. This is a measure of trustworthiness for the route source. For example, directly connected routes have the lowest distance, while routes learned from dynamic protocols or static configuration have higher values. Another component is the metric. Metrics vary depending on the routing protocol. They may be based on hop count, bandwidth, delay, or other factors. Metrics help routers choose the best path when multiple options exist. Finally, the routing table indicates whether the route is directly connected, static, or learned dynamically from a routing protocol like OSPF, EIGRP, or RIP. In a Cisco routing table, each route begins with a short code that tells you how the route was learned. Reading these codes quickly explains the source and type of every entry. Common codes you'll see: C, connected. The network is directly attached to a local interface. L, local. The exact IP assigned to a local interface. S, static. A route manually configured by an administrator. A candidate default route, commonly the .0.0.0 static. R, learned via the RIP routing protocol. O, OSPF intra-area, learned within the same OSPF area. OEA, OSPF inter-area, learned from a different OSPF area. OE1, OE2, OSPF external types 1 and 2. OM1, ON2, OSPF NSSA external types 1 and 2. D, EIGRP internal, learned via IGRP within the same autonomous system. DEX EIGRP external, redistributed into EIGRP from another source. B, BGP, learned via the border gateway protocol. A few less common but possible codes. I, routes learned via the ISIS protocol. O, ODR, on-demand routing and small hub and spoke setups. Remember that the code describes the source of the route. The rest of the entry shows the prefix, the administrative distance and metric, and either the next hop or the outgoing interface. Being fluent with these codes lets you interpret the routing table at a glance and understand how each path entered the router. In a routing table, the prefix represents the destination network. It tells the router which group of IP addresses a particular route applies to. The prefix is made up of two parts. the network address and the prefix length. The prefix length, written as a slash followed by a number, shows how many bits belong to the network portion of the address. For example, a prefix length of /24 means the first 24 bits define the network, leaving the last 8 bits for hosts. A longer prefix length, like /30, defines a much smaller subnet with only a few usable addresses. Routers compare the destination address in a packet against all prefixes in the routing table. The router uses the longest prefix match rule, which means the most specific prefix, the one with the greatest number of matching bits, is chosen to forward the packet. The network mask works hand in hand with the prefix to define the boundary between the network portion and the host portion of an IP address. In IPv4, the mask is shown in dotted decimal format, such as 255.255.255.0 for a /24 prefix. Each 255 represents 8 bits set to 1, while zeros represent host bits. In IPv6, the mask is expressed only as the prefix length, such as /64. The network mask is critical for determining whether two devices are in the same subnet. If the network portions of their addresses match, based on the mask, they can communicate directly. If not, traffic must be sent to a router. Routers also rely on the network mask in the routing table. It defines the size of the destination network and works with the longest prefix match rule to select the most specific route available. In a routing table, the next hop tells the router where to send a packet next on its journey to the destination. When a router receives a packet, it looks at the destination IP address and searches its routing table for the best match. The routing table entry includes the next hop, which is usually the IP address of a neighboring router. The packet is then forwarded to that device, which continues the process until the packet reaches its final destination. Sometimes, instead of a next hop address, the routing table shows an outgoing interface. This means the router can send the packet directly out of that interface toward the destination, such as when the network is directly connected. The next hop is critical for building an end-to-end path across multiple networks. Each router only needs to know the next step, not the entire path. Together, these next hop decisions move packets across the internet or enterprise network. Administrative distance, often called AD, is a value that routers use to rate the trustworthiness of a route. When multiple routes to the same destination exist, the router chooses the one with the lowest administrative distance. Different route sources have different default values. Directly connected networks have the lowest AD of 0, meaning they are always preferred. Static routes have an AD of 1, unless changed by the administrator. Dynamic routing protocols have higher values depending on the protocol. For example, EIGRP has an AD of 90, OSPF has 1 or 10, and RIP has 120. External routes learned through redistribution usually have even higher values. Administrative distance is only compared when 2 or more routes to the same destination exist. If one route has a lower AD, it will be installed in the routing table, even if another protocol provides a different path. A metric is a value that routing protocols use to decide which path is best when multiple routes to the same destination exist. While administrative distance chooses between different route sources, the metric is used within a single routing protocol to select the most efficient path. Different routing protocols calculate metrics in different ways. RIP uses hop count. The path with the fewest hops is preferred. OSPF uses cost, which is based on interface bandwidth. Higher bandwidth links have lower cost. EIGRP uses a composite metric that considers bandwidth and delay and can also factor in reliability and load if configured. BGP uses attributes such as path length, policy, and preference rather than a simple numeric metric. If 2 or more routes have the same metric, many protocols allow equal cost load balancing, meaning traffic can be distributed across multiple paths of equal quality. The gateway of last resort is the path a router uses when it doesn't have a more specific route to a destination in its routing table. It acts as a safety net, ensuring that unknown traffic can still be forwarded. In Cisco devices, the gateway of last resort is shown in the routing table as the default route. In IPv4, this is written as all 0/0, and in IPv6 as :/0. A default route can be configured manually as a static route, or it can be learned dynamically from a routing protocol. For example, A router on the edge of a network might have a default route pointing to the internet service provider. This way, any traffic for unknown destinations is forwarded to the ISP. Without a gateway of last resort, packets for unknown destinations are simply dropped, since the router would have no path to forward them. When a router receives a packet, it follows a step-by-step process to decide where to send it next. First, the router looks at the destination IP address in the packet. It then compares that address against the entries in its routing table. The router applies the longest prefix match rule. This means it chooses the most specific route, the one with the greatest number of matching bits in the prefix, rather than simply the first match it finds. If multiple routes match with the same prefix length, the router looks at the administrative distance. The route with the lowest administrative distance is considered the most trustworthy and is installed in the routing table. If the routes come from the same source, the router then looks at the metric provided by the routing protocol to determine the best path. Some protocols may even allow load balancing if multiple equal cost routes exist. If no match is found at all, the router forwards the packet to the gateway of last resort if one is configured. If there is no default route, the packet is dropped. The longest prefix match is the fundamental rule routers use when selecting the best route for a packet. When a router receives a packet, it compares the destination IP address against all entries in the routing table. Each route has a prefix, which defines how many bits of the address must match. The router always chooses the route with the longest matching prefix, meaning the most specific route. For example, if one entry matches the first 16 bits and another matches the first 24 bits, the 24-bit match is chosen because it is more specific. This ensures that packets take the most accurate path available. A broad prefix, like a default route, only applies if no more specific routes are found. In summary, the longest prefix match rule guarantees that routers forward packets using the most specific and precise route in the routing table. When multiple routing sources provide paths to the same destination, routers use administrative distance to decide which one to trust. Administrative distance is a value that represents the reliability of the source of a route. The lower the value, the more preferred the route. For example, directly connected networks have an AD of 0, meaning they are always trusted first. Static routes have an AD of 1, unless changed by the administrator. Dynamic routing protocols vary. EIGRP uses 90, OSPF uses 110, and RIP uses 120. External routes, such as those redistributed into a protocol, often have higher AD values. When the router sees multiple routes to the same prefix, it installs the one with the lowest administrative distance in the routing table. The others are ignored, even if they point to valid paths. When a routing protocol learns multiple possible paths to the same destination, it uses a metric to decide which path is the best. Each routing protocol has its own way of calculating metrics. RIP uses hop count. The path with the fewest router hops is chosen. OSPF uses cost, which is based on interface bandwidth. Higher bandwidth equals lower cost. EIGRP uses a composite metric that considers bandwidth and delay by default, and can also factor in load and reliability if configured. BGP doesn't use a simple numeric metric. Instead, it uses path attributes like AS path length, local preference, and policy-based decisions. If two or more paths have the same metric, many protocols allow equal-cost multipath routing, meaning the router can install multiple routes and share the traffic among them. Static routing is the process of manually defining routes in a router's routing table. Unlike dynamic routing protocols, static routes do not change unless the administrator reconfigures them. To configure an IPv4 static route, you specify the destination network, the subnet mask or prefix length, and either the next hop address or the outgoing interface. Once configured, the router installs the route into the routing table. IPv6 static routes work the same way. The administrator defines the destination prefix and the next hop or interface. Because IPv6 addresses are longer, the prefix notation is used consistently, such as /64. Verification is done by checking the routing table to confirm the static route is present. You can also use ping or tracer route to test connectivity along the path. Static routes can also be configured as default routes, which act as the gateway of last resort. In IPv4, this is all 0/0. In IPv6, it is :/0. A default route is a special type of static route that acts as a catch-all path for any traffic that does not have a more specific match in the routing table. In IPv4, the default route is written as all 0/0. In IPv6, it is written as :/0. These notations mean any destination network. When a packet arrives and no other routes match, the router uses the default route to forward it. This is especially useful for edge routers that connect to the internet, where it would be impractical to store every possible destination network in the routing table. Instead, the router can simply forward all unknown traffic to the ISP through the default route. Default routes can be configured manually as static routes, or they can be learned dynamically from a routing protocol. A network route is a static route that points to an entire subnet or network. Instead of handling all traffic like a default route, it applies only to a specific destination prefix. For example, an administrator can configure a network route for a subnet such as /24 in IPv4 or /64 in IPv6. This tells the router that any traffic with a destination inside that subnet should be forwarded to a particular next hop or out a specific interface. Network routes are useful for directing traffic to known networks within an organization. They can also be used for summarization, where one route entry covers multiple smaller subnets, reducing the size of the routing table. A host route is the most specific type of route in a routing table. Instead of pointing to an entire network, it points to a single IP address. In IPv4, a host route is written with a prefix length of /32, which matches exactly one address. In IPv6, a host route uses /128. Host routes are useful when traffic to a single device needs to be directed to a specific next hop or interface. For example, you might configure a host route for a management server, a loopback address, or a special network service. Because host routes are the most specific, they always take priority under the longest prefix match rule. Even if a broader network route exists, the host route will be chosen for that exact address. A floating static route is a backup static route that only becomes active if the primary route fails. This is achieved by assigning the static route a higher administrative distance than the primary route. Since routers always prefer the lowest administrative distance, the floating static route stays hidden in the routing table until it's needed. For example, you might configure a dynamic routing protocol as the primary path with an administrative distance of 90. Then you set up a floating static route with an administrative distance of 100. Under normal conditions, the dynamic route is used, but if that route disappears, the static route floats up and takes over, keeping traffic flowing. Floating static routes are often used for redundancy, such as backing up an internet connection or providing a secondary path between branch and headquarters networks. OSPF v2, or Open Shortest Path First version 2, is a dynamic routing protocol used for IPv4 networks. It is a link state protocol, which means routers share detailed information about their links and then calculate the shortest path using the Dijkstra algorithm. In a single area OSPF design, all routers are placed into area 0, also called the backbone area. This simplifies configuration and is common in small to medium-sized networks. To configure OSPF, routers are assigned a process ID and interfaces are added to the OSPF process. Each interface advertises the networks it is connected to, and routers exchange information using messages called LSAs, or link state advertisements. Once OSPF neighbors form adjacencies, they build a synchronized link state database. From this database, each router independently calculates the best path to every destination and installs those routes into its routing table. Verification includes checking that neighbor relationships are established, confirming the correct networks appear in the routing table, and ensuring routes are updated automatically if links go up or down. In OSPF, routers must first form neighbor adjacencies before they can exchange routing information. This is the process where two routers on the same network segment recognize each other and begin sharing link state data. The process starts when routers send hello packets on OSPF-enabled interfaces. If the parameters in the hello packets match, such as area ID, timers, subnet, and authentication, the routers become neighbors. Once neighbors, OSPF goes through several states. Down, no hellos have been received. In it, a hello has been seen from the neighbor, but two-way communication is not yet established. Two-way, both routers have exchanged hellos and recognized each other. On broadcast networks, this is the state where a designated router and backup designated router are elected. Start and exchange. Routers begin exchanging database descriptions, essentially summarizing their link state databases. Loading. Routers request and receive specific LSAs they are missing. Full. The adjacency is complete, and the router's databases are fully synchronized. Only once routers reach the full state do they install OSPF routes into the routing table. In OSPF, a point-to-point network type refers to a directly between exactly two routers. This is one of the simplest and most efficient OSPF network types. On a point-to-point link, there is no need to elect a designated router or backup designated router since only two devices share the segment. This reduces overhead and speeds up convergence. When OSPF is enabled on a point-to-point interface, the routers send hello packets, form a neighbor adjacency, and then exchange link state information directly with each other. The process is fast and straightforward. Point-to-point links are common on WAN connections, such as serial lines, Ethernet links configured as point-to-point, or modern high-speed links between routers. In OSPF, a broadcast network type is used on multi-access networks, such as Ethernet LANs, where multiple routers can be connected to the same segment. To reduce unnecessary traffic, OSPF uses a designated router, or DR, and a backup designated router, or BDR. Instead of every router forming a full adjacency with every other router, all routers form adjacencies only with the DR and BDR. This creates a hub-and-spoke relationship that minimizes overhead. The DR is responsible for generating and distributing LSAs for the segment. If the DR fails, the BDR automatically takes over, ensuring continuity. The election of the DR and BDR is based on the OSPF priority setting on each router's interface. If priorities are equal, the router with the highest router ID is chosen. Administrators can influence the election by adjusting the priority values. In OSPF, each router is identified by a unique router ID, often abbreviated as RID. This ID is used to distinguish routers within the OSPF domain and plays a key role in operations like DR-BDR elections and LSA generation. The router ID is a 32-bit value, written in the same format as an IPv4 address. It doesn't have to be an actual IP address on the router, but it must be unique within the OSPF network. OSPF selects the router ID automatically using a specific order. 1. If a router ID is manually configured, that value is used. If not, the highest IP address on a loopback interface is chosen. 3. If no loopbacks exist, the highest active IP address on a physical interface is used. Because the router ID is chosen at OSPF startup, a change in IP addresses won't affect it until the OSPF process is restarted or the router ID is reconfigured manually. In an IP network, end devices typically send all traffic for remote destinations to a default gateway. If that gateway fails, the devices lose connectivity even if another router is available. To solve this problem, networks use first hop redundancy protocols, or FHRPs. The purpose of FHRPs is to provide gateway redundancy. They allow multiple routers to work together and present a single virtual gateway IP address to hosts. If one router fails, another takes over automatically, keeping traffic flowing without requiring any reconfiguration on the hosts. Different protocols provide this function. HSRP, Hot Standby Router Protocol, is Cisco's proprietary FHRP. One router is active, another is in standby, and they share a virtual IP. If the active fails, the standby takes over. VRRP, Virtual Router Redundancy Protocol, is an open standard. It works similarly to HSRP but is supported across multiple vendors. GLBP, Gateway Load Balancing Protocol, is Cisco specific. Unlike HSRP and VRRP, it provides both redundancy and load balancing, allowing multiple routers to actively forward traffic while still offering failover. So far, we've covered network fundamentals, access, and connectivity. The next domain is IP services, which accounts for a portion of the CCNA exam focused on the extra functions that support real-world networking. This includes concepts like network address translation, DHCP, and DNS. It also covers services for monitoring and troubleshooting, such as SNMP, syslog, and NetFlow. Security-related features, including ACLs and QoS, are also part of this domain. Network address translation, or NAT, is a service that translates private IP addresses used inside a network into public IP addresses that can be used on the internet. The most common type is inside source NAT, where the internal or inside source address is translated as traffic leaves the network. There are two main methods. Static NAT creates a one-to-one mapping between a private IP address and a public IP address. This is often used for servers that must always be reachable from the outside, such as a web server or mail server. The translation never changes. Dynamic NAT with pools uses a group of public addresses. When an internal device sends traffic, it is temporarily mapped to one of the addresses from the pool. Once the session ends, the address can be reused by another device. This allows many private hosts to share a limited pool of public addresses, but each connection still uses a unique public IP. Verification of NAT includes checking the translation table on the router. The table shows which inside addresses are being translated and what public addresses they are mapped to. Network Time Protocol, or NTP, is used to synchronize the clocks of devices across a network. Accurate timekeeping is important for logs, authentication, and coordination of events. In server mode, a device provides the official time to other devices. This server might be synchronized with a higher-level source, such as an internet time server or a GPS clock, to ensure accuracy. In client mode, a device receives the time from an NTP server and adjusts its own clock accordingly. Most network devices are NTP clients, ensuring they all stay synchronized with the same reference time. NTP uses a hierarchical system of stratum levels. Stratum 1 devices are directly connected to an authoritative time source. Stratum 2 devices synchronize from Stratum 1, and so on. The higher the stratum number, the further away it is from the original source. Verification involves checking that the device is synchronized to the correct NTP server and that the offset, or time difference, is within acceptable limits. Two of the most important IP services in a network are DHCP and DNS. They make it possible for devices to join and use the network without manual configuration. DHCP, or Dynamic Host Configuration Protocol, automatically assigns IP addresses and related settings to devices. When a device connects, it sends a request, and the DHCP server responds with an IP address, subnet mask, default gateway, and often DNS server information. This eliminates the need for manual configuration and reduces errors. DNS, or Domain Name System, translates human-readable names like example.com into IP addresses that computers use to communicate. Without DNS, users would have to remember numeric addresses instead of names. DNS servers handle this translation, making the Internet and enterprise applications user-friendly. Together, DHCP and DNS are tightly integrated. DHCP assigns devices their IP information, including which DNS server to use, and DNS resolves the names those devices need to reach. SNMP is used to monitor and manage devices across a network. It provides administrators with visibility into performance, availability, and configuration. SNMP works with three main components: managers, centralized systems, often called network management stations, that request and collect information; agents, software running on network devices like routers, switches, and servers, which respond to requests and send updates; MIBs, or management information bases, structured databases of information that define what can be monitored or controlled, such as interface status, CPU usage, or error counts. SNMP uses two key methods of communication: polling, where the manager requests data from the agent at regular intervals; traps, where the agent proactively sends alerts to the manager when something significant occurs, like a link going down. Different versions of SNMP exist. SNMP v1 and v2c are older and use community strings for authentication. SNMP v3 adds encryption and stronger authentication, making it the preferred version for modern networks. Syslog is a standard protocol used by network devices to send log messages to a central server. It provides a way to collect, store, and analyze system events across the entire network. Syslog messages include information about the facility and the severity level. The facility indicates which part of the system generated the message. For example, facilities may represent the kernel, the mail system, the authentication process, or local use categories. This helps administrators filter and organize logs. The severity level indicates the importance of the message. Levels range from 0 to 7, where 0 is the most critical and 7 is the least. 0, emergencies. The system is unusable. 1, alerts, immediate action required. 2, critical conditions. 3, errors. 4, warnings. 5, notifications, normal but significant events. 6, informational messages. 7, debugging details. By combining facilities and levels, administrators can fine-tune what logs are sent to the syslog server and how they are acted upon. DHCP, or Dynamic Host Configuration Protocol, allows devices to automatically receive IP addresses and related settings. Two common roles in DHCP configuration are the client and the relay. A DHCP client is any device configured to request its IP information from a DHCP server. Most end devices, like computers and phones, operate as clients. Network devices such as routers can also be configured as DHCP clients on specific interfaces, useful when connecting to an ISP. A DHCP relay is used when clients and the DHCP server are on different subnets. Normally, DHCP messages are broadcasts and do not cross routers. A relay agent listens for these requests and forwards them as unicast messages to the DHCP server. The server replies through the relay, ensuring clients can still get addresses even without being in the same subnet. Verification involves checking that clients successfully obtain addresses and that the relay is forwarding requests correctly. Administrators can also view lease information and monitor DHCP bindings. Quality of service, or QoS, ensures that critical applications receive the network performance they need, even when bandwidth is limited or congestion occurs. The key idea is per-hop behavior, meaning that at each device along the path, traffic is treated according to its classification and priority. The process involves several steps. Classification. Traffic is identified and grouped, often based on fields like source, destination, application, or protocol. Marking. Once classified, packets are marked with values such as DSCP in the IP header or SOS at layer 2. These markings tell downstream devices how to treat the traffic. Queuing. Traffic is placed into different queues based on priority. High priority queues, such as those for voice or video, are serviced more quickly than best effort queues. Congestion management. When too much traffic arrives, the device must decide how to handle it. Weighted scheduling ensures fair use while protecting critical traffic. Policing. Traffic is checked against defined limits. Excess packets may be dropped if the flow exceeds its allowed rate. Shaping. Unlike policing, shaping buffers excess traffic and sends it at a controlled rate, smoothing out bursts without dropping packets. Secure Shell, or SSH, is the standard method for securely managing network devices over a remote connection. Unlike Telnet, which sends data in plain text, SSH encrypts both authentication and session traffic, protecting it from eavesdropping. To configure SSH on a network device, administrators typically 1. Assign the device a host name and domain name. 2. Generate cryptographic keys for secure communication. 3. Enable SSH on the device's virtual terminal or V2I lines. 4. Create user accounts with strong authentication credentials. Once configured, administrators can connect using an SSH client, such as a terminal program, and manage the device's command line interface over the secure channel. Verification involves testing the connection to ensure SSH is enabled, confirming that Telnet is disabled or restricted, and checking that the session is properly encrypted. Two common protocols used in network operations are TFP and FTP. Both are used for transferring files, but they differ in features and use cases. TFTP, or Trivial File Transfer Protocol, is a simple, lightweight protocol. It uses UDP for transport and has minimal overhead. Because it doesn't provide authentication or encryption, it's often used only inside trusted networks. Common uses include transferring configuration files, software images, or boot files to routers, switches, and other devices. FTP, or File Transfer Protocol, is more advanced. It uses TCP for reliable delivery and supports authentication with usernames and passwords. Unlike TFTP, FTP allows directory navigation and supports larger, more complex transfers. However, standard FTP does not encrypt data, so credentials and files are sent in plain text. Secure versions like FTPS or SFTP are recommended when security is a concern. In practice, TFTP is often used for quick, lightweight transfers in network maintenance, while FTP is used when authentication or more robust file handling is required. So far, we've covered how networks are built, connected, and supported with IP services. The next domain is security fundamentals, which is critical for protecting modern networks. This section introduces key security concepts such as threats, vulnerabilities, and exploits. It covers common security features, including device hardening, access control, wireless protections, and Layer 2 security measures. You'll also learn about authentication, authorization, and accounting, along with secure management practices that prevent unauthorized access. In network security, it's important to understand the core concepts of threats, vulnerabilities, exploits, and mitigation. A threat is any potential danger to the network. This could be an attacker trying to steal data, a virus spreading through email, or even an insider misusing access. A vulnerability is a weakness that a threat can take advantage of. Examples include unpatched software, weak passwords, or misconfigured devices. An exploit is the actual act of taking advantage of a vulnerability. For instance, a hacker might exploit a bug in software to gain unauthorized access. Mitigation techniques are the countermeasures put in place to reduce risk. These can include strong password policies, software patching, firewalls, intrusion prevention systems, access controls, and employee training. A strong security program is not just about technology, it also involves people and processes. 3 important elements are user awareness, training, and physical access control. User awareness focuses on educating employees about potential threats. Users who understand phishing, social engineering, and safe browsing practices are less likely to become the weak link in security. Training goes deeper, providing structured instruction and practice. This might include security workshops, simulated phishing tests, or technical training for administrators on how to secure devices and systems. Training ensures that knowledge is reinforced and applied consistently. Physical access control protects the hardware itself. Even the strongest firewalls and encryption can be bypassed if someone can physically walk into a server room and plug in a device. Measures like locked rooms, security badges, cameras, and access logs help protect critical equipment. Controlling who can log into network devices is one of the most basic security measures. A simple way to do this is by using local passwords configured directly on the device. Administrators can set passwords for different types of access. The console line, used for local, direct connections. The VTY lines, used for remote management through Telnet or SSH. The enable password or secret, which controls access to privileged exec mode. When a user tries to connect, the device prompts for the appropriate password before granting access. For stronger security, an enable secret is preferred over an enable password because it is stored using a more secure hashing method. Verification involves testing access to the device from both console and remote sessions, confirming that passwords are required, and checking that the correct level of access is granted after authentication. Strong password policies are critical to securing network devices and user accounts. These policies define how passwords are created, managed, and enforced. Password management refers to how often passwords must be changed, how they are stored, and whether reuse of old passwords is allowed. For example, many organizations require regular password changes and prevent users from recycling recently used ones. Password complexity ensures that passwords are not easy to guess. A strong password usually combines uppercase and lowercase letters, numbers, and special characters. Longer passphrases are even better, as they are both secure and easier to remember. Beyond traditional passwords, many networks use password alternatives for stronger protection. Multi-factor authentication requires more than one form of proof, such as a password, plus a mobile app code or hardware token. Digital certificates can authenticate users and devices automatically, replacing the need for manual password entry. Biometrics, such as fingerprints or facial recognition, provide authentication based on something unique to the individual. Virtual private networks, or VPNs, provide secure communication over untrusted networks such as the Internet. One of the most common standards for VPNs is IPsec, or Internet Protocol Security. There are 2 primary types of IPsec VPNs, remote access and site-to-site. A remote access VPN allows individual users to securely connect to a private network from anywhere. For example, an employee working from home can use VPN software on their laptop to establish an encrypted tunnel to the corporate network. Once connected, they can access internal resources as if they were physically in the office. A site-to-site VPN connects entire networks together. For instance, a branch office can connect securely to headquarters by building an encrypted tunnel between their edge routers or firewalls. All traffic between the 2 sites is automatically encrypted, protecting data while it travels across the Internet. IPsec provides security through several key features: encryption, which protects the confidentiality of data; authentication, which verifies that traffic is from a trusted source; integrity checking, which ensures data hasn't been altered in transit; access control lists, or ACLs, are used to filter traffic and control which packets are allowed or denied as they move through a router or switch. They act like rules or checkpoints applied to network interfaces. There are two main types of ACLs. Standard ACLs filter traffic based only on the source IP address. They are simple but less precise, often applied close to the destination. Extended ACLs filter on multiple criteria, such as source address, destination address, protocol, and even port numbers. They provide much more control and are usually applied close to the source. When configuring an ACL, each rule is evaluated in order from top to bottom. As soon as a match is found, the action is taken, either permit or deny, and no further rules are checked. If no rules match, the implicit deny at the end blocks the traffic. Verification involves applying the ACL to an interface in the inbound or outbound direction and testing with real traffic. Administrators can also use commands to view hit counts on ACL entries, confirming which rules are being triggered. Layer 2 is often considered the most vulnerable part of the network, since attacks at this level can bypass higher-level protections. To defend against these risks, Cisco devices provide several key Layer 2 security features. DHCP snooping protects against rogue DHCP servers. It allows switches to define trusted ports where valid DHCP messages are expected. Any DHCP responses from untrusted ports are blocked, preventing attackers from assigning fake IP addresses to clients. Dynamic ARP inspection, or DI, protects against ARP spoofing attacks. It checks ARP packets against the DHCP snooping database to ensure that IP to MAC address bindings are legitimate. Invalid ARP messages are dropped, protecting clients from man-in-the-middle attacks. Port security limits which devices can connect to a switch port. It does this by restricting the number of MAC addresses allowed or by binding specific MAC addresses to the port. If an unauthorized device connects, the switch can take actions such as shutting down the port or dropping the traffic. Verification involves checking counters and logs to confirm that security policies are applied correctly and that legitimate traffic is unaffected. The AAA framework is a model to secure and manage access to network devices and resources. It stands for authentication, authorization, and accounting. Authentication is the process of verifying identity. It answers the question, who are you? This could be a username and password, digital certificate, or multi-factor login. Without authentication, anyone could attempt to access the network. Authorization defines what a user is allowed to do after they are authenticated. It answers, what can you access? For example, some users may only view system status, while administrators have permission to make configuration changes. Accounting tracks and records what the user does. It answers, what did you do? This includes logging commands executed, resources accessed, and session details. Accounting provides visibility for audits, compliance, and troubleshooting. Together, AAA ensures that only trusted users can access the network, that their actions are limited to approved tasks, and that all activities are logged. Wireless networks must be secured to protect data as it travels through the air. Over time, different security protocols have been developed, with each generation improving on the last. WPA, or Wi-Fi Protected Access, was introduced as an improvement over the older and vulnerable WEP standard. WPA used TKIP, a stronger encryption method, but it was only meant as a temporary solution. WPA2 became the long-term standard. It introduced the use of AES, or Advanced Encryption Standard, which provides strong protection against modern attacks. WPA2 supports both pre-shared keys for home networks and enterprise authentication with 802.1x and Radius for businesses. WPA3 is the latest generation. It strengthens encryption even further by requiring modern cryptographic standards and removing outdated ones. WPA3 also provides individualized data encryption between each client and the access point, making it harder for attackers to intercept traffic. In addition, it introduces stronger protections for weak passwords and improves security for open networks. One of the most common ways to secure a wireless LAN is by using WPA2 with a pre-shared key, or PSK. This method is widely used in small businesses and home networks because it's simple to set up and provides strong encryption. When configuring through a graphical user interface, such as a wireless controller dashboard or cloud-managed platform, the process usually involves a few key steps. 1. Create or edit a WLAN by assigning it a name or SSID that clients will use to connect. Select WPA2 as the security method. This ensures that AES encryption is used to protect data in transit. 3. Enter the pre-shared key, which is essentially the network password. This key must be entered by any client that wants to join the WLAN. 4. Apply and save the configuration, then verify that clients can connect successfully by entering the password. Administrators should choose a strong key that combines letters, numbers, and symbols to prevent guessing or brute force attacks. Traditional networks have relied heavily on manual configuration, logging into each device and making changes line by line. As networks have grown larger and more complex, this approach has become slow, error-prone, and difficult to scale. The automation and programmability domain introduces new ways of managing networks more efficiently. It covers how controllers, APIs, and configuration management tools allow administrators to make consistent changes across many devices. You'll also learn about concepts like model-driven programmability, the use of data formats such as JSON and YAML, and the role of software-defined networking in simplifying operations. Network automation changes the way administrators manage devices by replacing repetitive manual tasks with software-driven processes. Traditionally, administrators log into each device individually to configure settings or collect information. This approach is time-consuming and prone to human error. Automation reduces these risks by applying changes consistently across many devices at once. Automation also improves scalability. In large environments, thousands of routers, switches, and access points can be updated or monitored simultaneously. This would be nearly impossible with manual methods. Another benefit is speed and agility. Automated workflows allow networks to adapt quickly to business needs, such as provisioning new services, enforcing security policies, or responding to outages. Finally, automation increases visibility and accuracy. Scripts and tools can collect data from devices in real time, ensuring that configurations stay aligned with standards and reducing misconfigurations. In a traditional network, each device, such as routers and switches, is configured and managed individually. The control plane, which makes decisions about forwarding traffic, and the data plane, which moves the traffic, both reside on the device itself. While this model works, it becomes complex as networks grow, since every change must be applied manually to each device. In a controller-based network, the control plane is centralized. A network controller manages policies, configurations, and decisions for many devices at once. The devices, sometimes called network fabric, focus on forwarding data, while the controller handles intelligence and automation. This centralization brings several advantages. Simplified management. Administrators can push changes from a single platform instead of logging into each device. Consistency. Policies like security rules or QoS settings can be applied uniformly across the entire network. Programmability. Controllers expose APIs, allowing automation tools and scripts to configure and monitor the network programmatically. Faster adaptation. Networks can respond more quickly to changes in demand or new applications. In modern networks, software-defined architecture separates the intelligence of the network from the underlying hardware. This is often described in terms of underlay, overlay, and fabric. The underlay is the physical network, the switches, routers, cabling, and wireless connections that provide basic connectivity. Its main job is to move packets from one point to another. The overlay is a virtual network built on top of the underlay. It uses technologies like tunneling or encapsulation to create logical paths independent of the physical layout. This allows administrators to define networks and policies in software without being constrained by physical topology. The fabric is the combination of both underlay and overlay, controlled by a central controller. The fabric provides end-to-end connectivity and policy enforcement, making the network easier to automate and manage. In Cisco environments, examples include SD-Access and SD-WAN. This architecture allows networks to be more agile, secure, and scalable. Policies can be applied consistently, and the network can adapt quickly to changing business needs. In traditional networks, each device contains both the control plane and the data plane. The control plane is responsible for making decisions. It runs protocols like OSPF or EIGRP, builds routing tables, and determines the best path for traffic. The data plane, also called the forwarding plane, is responsible for actually moving packets based on those decisions. In a software-defined network, these two planes are separated. The control plane is centralized in a network controller, while the data plane remains on the individual devices. The controller calculates the policies and forwarding decisions, then pushes them to the devices, which simply forward packets as instructed. This separation makes networks easier to automate, more consistent, and faster to adapt. Instead of configuring dozens or hundreds of devices manually, administrators can make changes in one place, and the controller ensures that all devices follow the same policy. In a software-defined network, controllers rely on APIs, or application programming interfaces, to communicate with both applications and devices. These are described as northbound and southbound APIs. Southbound APIs connect the controller to the network devices, the switches, routers, and access points that forward traffic. Through these APIs, the controller sends instructions such as forwarding rules, QoS settings, or security policies. Common southbound protocols include OpenFlow, NetConf, and vendor-specific interfaces. Northbound APIs connect the controller to higher-level applications and management tools. These allow software such as monitoring systems, automation scripts, or business applications to request information from the controller or push new policies into the network. Northbound APIs are often REST-based and use formats like JSON or XML. The combination of northbound and southbound APIs allows the controller to act as the central brain of the network. Applications talk to the controller through northbound APIs, and the controller enforces those policies on devices through southbound APIs. Modern networks generate massive amounts of data, logs, telemetry, traffic flows, and security alerts. Analyzing all of this manually is impossible. This is where artificial intelligence, AI, and machine learning, ML, come in. Machine learning refers to algorithms that learn patterns from data and improve over time without being explicitly programmed. In networking, ML can analyze traffic trends, detect anomalies, and predict failures before they happen. For example, it might recognize that a link is likely to fail soon based on rising error rates. Predictive AI builds on this by using historical and real-time data to forecast future behavior. In operations, predictive AI can warn about bandwidth saturation, application slowdowns, or security threats, giving administrators a chance to act proactively instead of reactively. Generative AI goes further by creating new outputs based on patterns it has learned. In networking, generative AI can suggest configuration changes, generate troubleshooting steps, or even create optimized policies tailored to an environment. It can act as a co-pilot for network engineers, saving time and reducing errors. REST, or Representational State Transfer, is a common framework for APIs used in networking. REST-based APIs allow applications to interact with network controllers and devices over standard web protocols. Several characteristics define how REST APIs work. Authentication. REST APIs often require authentication before access is granted. This may be as simple as an API key or as secure as token-based systems like OAuth. Some implementations also use basic authentication with usernames and passwords. CRUD operations. REST APIs are built around 4 basic functions, often summarized as CRUD: create, read, update, and delete. These map directly to how resources such as device configurations or policies are managed. HTTP verbs. REST uses standard HTTP methods to perform CRUD operations. POST is used to create new resources. GET is used to read or retrieve information. Put or patch is used to update an existing resource. Delete removes a resource. Data encoding. REST APIs exchange data in standard formats that are easy for both humans and machines to understand. The most common is JSON, but XML is also supported in some cases. JSON is lightweight and widely used in modern network programmability. As networks grow larger and more complex, automation tools are needed to keep configurations consistent and repeatable. 2 popular mechanisms for this are Ansible and Terraform. Ansible is an automation tool that uses simple, human-readable playbooks written in YAML. It connects to devices, usually over SSH or APIs, and pushes configurations directly. Ansible is agentless, meaning no special software needs to be installed on the network devices. It's often used for tasks like deploying VLANs, updating access control lists, or applying security patches across many devices at once. Terraform is an infrastructure as code tool that describes infrastructure in a declarative way. Instead of pushing step-by-step instructions, you define the desired end state in configuration files. Terraform then builds or updates the environment to match that state. It's widely used for cloud networking, virtual machines, and hybrid environments, but it can also integrate with network devices through providers. Together, these tools bring consistency, version control, and scalability to network management. They reduce manual errors and allow networks to be treated like code, easy to share, review, and roll back when needed. JSON or JavaScript object notation is one of the most common formats used in network automation and programmability. It's lightweight, easy to read, and widely supported by APIs and automation tools. JSON data is made up of a few key components. Objects. Enclosed in curly braces, objects contain one or more pairs of keys and values. For example, an object might describe a device with properties like hostname or IP address. Keys, the names inside an object. Keys are always written as strings and quotation marks, such as hostname. Values, the data assigned to a key. Values can be strings, numbers, booleans like true or false, arrays, or even another object. For example, IP 192.168.1.1. Arrays, ordered lists of values enclosed in square brackets. Arrays are useful for representing multiple items, like a list of interfaces or VLANs. Each key value pair is separated by a colon, and pairs are separated by commas. The structure makes JSON both flexible and easy for machines to parse. Narrated lab scenarios. Scenario 1, basic router and switch setup. When you first bring a Cisco router or switch online, the goal is to give it a proper identity and prepare it to communicate on the network. The setup usually begins by assigning the device a host name. By default, Cisco devices might just be called router or switch, but giving them a meaningful name makes it easier to know which one you're working on, especially in larger environments. Next comes securing access. Administrators set up passwords so that only authorized people can connect to the device. This includes protecting the local console port for direct access, securing remote sessions like Telnet or SSH, and setting a password to reach privileged modes where important changes are made. After security is in place, the device needs to be given an IP address on one or more interfaces. This allows it to communicate with other devices on the network. Along with the address, the interface must be enabled so that traffic can actually pass. Finally, once everything is configured, the changes are saved so they remain in effect after a reboot. This ensures that the work isn't lost and the device will start up correctly in the future. Scenario 2, VLANs and inter-VLAN routing. In a modern switch network, one of the most common tasks is setting up VLANs, or virtual local area networks. VLANs allow you to divide a single switch into multiple logical networks, so different groups of devices can be kept separate even if they share the same hardware. The process starts by creating VLANs and giving them names that match their purpose. For example, you might create one VLAN for the sales department and another for the engineering team. Each VLAN becomes its own broadcast domain, isolating traffic between groups. Next, switch ports are assigned to the appropriate VLANs. This means that when a computer or printer is plugged into that port, it automatically becomes part of the correct VLAN. Ports for phones can even be set to carry both a voice VLAN and a data VLAN at the same time. But VLANs on their own cannot talk to each other. To allow communication between VLANs, you need inter-VLAN routing. This can be done with a router using a router on a stick setup or by using a layer 3 switch that can perform routing directly. This step allows users in one VLAN to reach servers or resources in another VLAN when needed. Finally, the setup is verified to make sure devices in the same VLAN can communicate and that traffic between VLANs flows correctly through the router or switch. Scenario 3, static routing and default routes. Routers are responsible for directing traffic between different networks. One of the simplest ways to teach a router where to send traffic is through static routing. With static routing, the administrator manually defines the path. For example, if one router is directly connected to a remote network, you can add a static route that points to the next hop router or to the correct interface. This tells the router, if you see traffic for that network, send it this way. Static routes are reliable and predictable because they never change on their own. However, they require manual updates if the network topology changes. That's why they are often used in small networks or as a backup to dynamic routing protocols. In addition to specific static routes, most networks also configure a default route. The default route acts like a catch-all instruction. If the router doesn't have a more specific path for the destination, it forwards the traffic along the default route, often toward the Internet gateway. Verification is an important part of routing. Administrators check the routing table to make sure the static and default routes are installed and then test by sending traffic across the network to confirm that it takes the expected path. Scenario 4, NAT configuration for Internet access. Most private networks use internal IP addresses that cannot travel across the public Internet. To allow users to reach external websites and services, we need network address translation, or NAT. NAT works by translating private IP addresses into public ones. There are a few common types. Static NAT creates a one-to-one mapping. For example, a web server on a private address can be mapped to a single public IP, making it accessible from outside the network. Dynamic NAT uses a pool of public addresses. When an internal device needs Internet access, it is temporarily assigned one of the available public addresses. NAT overload, also called port address translation or PAT, is the most common in home and business environments. Here, many devices share a single public IP address. The router keeps track of each session by assigning unique port numbers, so multiple devices can be online at the same time. In practice, NAT allows an entire office or even a large organization to connect to the Internet while using only a handful of public IP addresses. Verification usually involves checking translation tables on the router to confirm that internal addresses are being mapped correctly, and testing by browsing the Internet or reaching outside services. Scenario 5, basic OSPF setup and verification. In larger networks, manually configuring static routes quickly becomes impractical. That's where dynamic routing protocols come in. One of the most widely used is OSPF, or Open Shortest Path First. OSPF allows routers to automatically learn about each other's networks and build a shared view of the topology. Instead of manually typing in routes, the routers exchange information and calculate the best paths on their own. The process starts with neighbor relationships. When two OSPF-enabled interfaces are on the same network, they exchange hello messages. If their settings match, they form an adjacency. This is the foundation of OSPF communication. Once neighbors are established, routers share details about the networks they know. Each router uses this information to build a link state database, which is like a detailed map of the network. From this map, OSPF calculates the shortest paths and installs them into the routing table. Verification in an OSPF lab often involves checking that neighbors are formed correctly, confirming the networks appear in the routing table, and testing connectivity between devices in different parts of the topology. At the heart of networking theory are two models that describe how data moves across a network: the OSI model and the TCP/IP model. The OSI model, or Open Systems Interconnection model, has 7 layers. From top to bottom they are: 1. Application, where users interact with applications like web browsers or email. 2. Presentation, responsible for data formatting, compression, and encryption. 3. Session, manages communication sessions between devices. 4. Transport, ensures reliable delivery with protocols like TCP and UDP. 5. Network, determines the best path for data, using IP addresses and routing. 6. Data link, provides node-to-node delivery using MAC addresses and switches. 7. Physical, transmits raw bits over cables, fiber, or wireless signals. While the OSI model is theoretical, the TCP/IP model is more practical. It has 4 layers: 1. Application, combining OSI's top 3 layers. 2. Transport, same role as OSI, with TCP and UDP. 3. Internet, matching OSI's network layer, responsible for IP addressing and routing. 4. Network access, combining data link and physical layers. These two models align closely. For example, a web request begins at the application layer with HTTP, uses TCP at the transport layer, relies on IP at the network layer, and finally transmits over Ethernet at the data link and physical layers. The physical medium of a network is just as important as the protocols that run on top of it. Understanding Ethernet standards and cable types is a key part of networking. Copper cabling. Most local networks rely on twisted pair copper cabling. Common categories include Cat5e, supports speeds up to 1 gigabit per second over 100 meters. Cat6 supports 1 gigabit at 100 meters and up to 10 gigabits at shorter distances, typically 55 meters. Cat6a, designed for 10 gigabits up to 100 meters with improved shielding. Copper cables can be straight through or crossover. Straight through cables connect devices of different types, such as a PC to a switch. Crossover cables connect similar devices, like switch to switch, though most modern equipment supports auto MDI-NX, eliminating the need for crossovers. Rollover cables, often flat and light blue, are console cables used to connect a computer to a device's management port. Fiber cabling. For longer distances and higher speeds, fiber optic cables are used. Single-mode fiber has a small core and uses laser light, supporting extremely long distances, often measured in kilometers. Multi-mode fiber has a larger core and uses LED light, supporting shorter distances, typically up to a few hundred meters, but at lower cost. Practical use. In practice, copper cabling dominates inside buildings and data centers, while fiber is preferred for backbone links, long-distance connections, and high-speed requirements. At layer 2 of the OSI model, data is packaged into Ethernet frames. Understanding the structure of these frames helps explain how switches move traffic and how errors are detected. An Ethernet frame has several key parts: preamble and start frame delimiter. These come first, providing synchronization so devices know when a frame begins. Destination MAC address, the unique hardware address of the intended recipient. This tells the switch where to forward the frame. Source MAC address, the hardware address of the sender. Switches use this to learn which devices are connected to which ports. Ether type or length field identifies what kind of payload the frame is carrying, such as IPv4, IPv6, or ARP, or indicates the size of the data. Payload, the actual data being delivered, which could be an IP packet or other higher layer information. Frame check sequence, or FCS, a checksum value calculated by the sender. The receiver recalculates it to detect errors. If the values don't match, the frame is discarded. Ethernet frames have a minimum size of 64 bytes and a maximum size of 1518 bytes, not including special options like VLAN tagging, which adds additional fields. Subnetting is one of the most important skills in networking. It defines how IP addresses are divided into networks and hosts. While the math can feel intimidating at first, there are shortcuts and tricks that make it easier. An IPv4 subnet is defined by a prefix length written in CIDR notation, such as /24. The prefix length tells us how many bits are reserved for the network portion and how many are left for hosts. To quickly calculate the number of host addresses in a subnet, use the formula 2 to the power of n minus 2, where n is the number of host bits. The -2 accounts for the network ID and the broadcast address. For example, a /24 leaves 8 host bits. 2 to the power of 8 is 256 minus 2 equals 254 usable addresses. A30 leaves 2 host bits. 2 to the power of 2 is 4 minus 2 equals 2 usable addresses. Another shortcut is to memorize common subnet sizes. /24 total addresses, 254 usable. /26 equals 64 total, 62 usable. /28 equals 16 total, 14 usable. /34 total, 2 usable. When asked to find the network ID, remember to round the given IP address down to the nearest block size. For example, in a /26 network, the block size is 64. An address like 192.168.1.77 would belong to the 192.168.164 network, with a broadcast of 192.168.1127. Subnetting becomes faster with practice, but these shortcuts, using powers of 2, memorizing common masks, and rounding down to block sizes, make it much easier during exams or troubleshooting. Beyond the fundamentals, it helps to understand some additional security concepts that often appear in networking discussions and on the CCNA exam. First, let's compare symmetric and asymmetric encryption. Symmetric encryption uses the same key for both encryption and decryption. It's fast and efficient, but the challenge is securely sharing the key. Asymmetric encryption uses a pair of keys, a public key for encryption and a private key for decryption. This method solves the key distribution problem and is used in protocols like SSL and TLS. Next, consider IDS versus IPS. An intrusion detection system, or IDS, monitors traffic for suspicious activity and alerts administrators but does not block the traffic. An intrusion prevention system, or IPS, actively blocks or drops malicious traffic in real time. Another distinction is between hashing, encryption, and encoding. Hashing creates a fixed length value from input data and is used for integrity checks. It cannot be reversed. Encryption secures data by scrambling it into unreadable form, but it can be decrypted with the correct key. Encoding simply converts data into another format for compatibility, like base64. It is not meant for security. Finally, a key mindset in modern networking is zero trust. This principle assumes no user or device is trusted by default, even if it is inside the network. Every request must be verified through authentication and authorization before access is granted. You've reached the end of this CCNA study and relaxation session. We've walked through Cisco IOS commands, reviewed well-known port numbers, covered the official exam objectives, and explored scenarios and deep dives. Each step was designed to help the knowledge sink in slowly, whether you were actively studying or just letting it play in the background. Remember, learning doesn't always have to be intense or rushed. Sometimes, simply listening and absorbing is enough to strengthen your understanding over time. If you're using this as part of your study routine, you can return to any section whenever you need a refresher. And if you're using it to fall asleep, let the calm repetition of these ideas help your mind stay connected to your goals, even in rest. Thank you for listening, and may your studies and your sleep both be peaceful and productive.